Hello there, and welcome. Tonight I want to take you somewhere far from the familiar glow of city lights, far from the warmth of our sun, into the profound darkness that stretches between the outermost planets and the edge of what we call home. Settle in, make yourself comfortable, and let your breathing slow as we begin this journey together. You know, there's something deeply peaceful about contemplating the vast spaces that surround us. Those quiet realms where time moves differently, where a single orbit might take thousands of years, and where the darkness is so complete that it becomes almost tangible, like a soft blanket draped across infinity. It's a question that might seem impossible to answer, perhaps even impossible to ask properly. But what if I told you that in the outer reaches of our solar system, there might be connections we've never imagined? Threads linking objects separated by billions of miles and millions of years? What if a comet that briefly graced our skies was actually a messenger, sent from the edge of darkness by a planet we've never seen? Tonight, we're going to explore this gentle mystery together, you and I, and we're going to do it slowly, thoughtfully, letting each idea settle like stardust in the quiet corners of your mind. Consider this for a moment. As you lie there, perhaps with your eyes closed, the Earth beneath you is spinning at over 1,000 miles per hour, carrying you through space as we orbit our sun at 67,000 miles per hour. And yet, from your perspective, everything feels perfectly still. This is the magic of cosmic scale, the way the universe can hold such tremendous motion and energy while maintaining an appearance of absolute tranquility. In the same way, our solar system, which seems so well mapped and understood, might be harboring secrets in its outer darkness, secrets that move so slowly, so quietly, that we're only just beginning to perceive their presence. The story we're about to explore begins with two mysteries that might, just might, be connected in ways that transform our understanding of the solar system we call home. The first mystery arrived as a visitor, a comet designated 3I Atlas, which appeared in our telescopes as a faint smudge of light, growing brighter as it approached the sun before quietly disintegrating into cosmic dust. The second mystery has never been directly observed at all, existing only as a gravitational ghost, a mathematical necessity that astronomers call Planet 9, a world perhaps 10 times the mass of Earth, orbiting in the frozen darkness beyond Neptune. Now, you might be wondering how these two mysteries could possibly be related. After all, comets visit our inner solar system all the time, ancient chunks of ice and dust that loop around the sun in long elliptical orbits. And the search for planets beyond Neptune has been going on for decades, ever since we discovered that Neptune itself was found through the careful observation of gravitational perturbations. But what makes this particular combination so intriguing is the timing, the trajectory, and the tantalizing possibility that we witnessed not just a random cosmic event, but a messenger dispatched from the edge of darkness by a world we've never seen. Let me paint you a picture of the scale we're dealing with here. If you could somehow shrink our entire solar system down so that the sun was the size of a basketball, Earth would be a tiny peppercorn about 26 yards away. Jupiter, our largest planet, would be a chestnut about 135 yards from that basketball sun. Neptune, the outermost known major planet, would be a coffee bean nearly half a mile away. But the hypothetical Planet 9, it would be somewhere between 1 and 3 miles from our basketball sun, so far away that even in this shrunken model, you'd need binoculars to see it. And the Oort cloud, that vast reservoir of comets that surrounds our entire solar system. In our model, it would stretch from about 50 miles to nearly 2,000 miles away from the basketball. These are distances that challenge our imagination, spaces so vast that light itself, the fastest thing in the universe, takes years to cross them. In these immense spaces, objects move with a different kind of grace than what we're used to seeing in our everyday lives. They don't hurry, they don't rush. A comet falling from the Oort cloud toward the sun might take millions of years to complete its journey. Planet 9, if it exists, might take between 10 and 20,000 years to complete a single orbit. These are timescales that dwarf human civilization, that make our entire recorded history seem like a single heartbeat in the life of the cosmos. And yet, despite these vast scales of space and time, gravitational forces still connect everything, creating an intricate dance where every object influences every other object, even across billions of miles. Perhaps you're already feeling it, that sense of peaceful insignificance that comes from contemplating cosmic scales. It's not a frightening feeling, not when you approach it gently. Instead, it's rather like standing at the edge of the ocean at night, listening to the waves and realizing that they've been breaking on this shore for millions of years before you arrived and will continue for millions of years after you're gone. There's something deeply comforting about being part of something so much larger than yourself, something that operates on timescales that make your worries and concerns seem refreshingly temporary. The connection we're exploring tonight between 3i Atlas and Planet 9 isn't something that anyone can prove definitively, at least not yet. It exists in the realm of possibility, in that fascinating space where science meets speculation, where data points towards something extraordinary but doesn't quite reach the level of certainty. This is actually where some of the most beautiful ideas in astronomy live, in this twilight zone between what we know and what we might discover. It's where Neptune lived before it was found, where Pluto existed before Clyde Tombaugh spotted it on those photographic plates, where countless exoplanets dwelt before we developed the technology to detect them. Think about the history of discovery in our solar system for a moment. For thousands of years, humans knew of only 5 planets beyond Earth, those visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. These were the wanderers, the stars that moved against the fixed background of the constellations. Then, in 1781, William Herschel discovered Uranus, doubling the size of our known solar system overnight. It was found not through some dramatic revelation, but through patient observation, through noticing something slightly different about what appeared to be just another star. Neptune followed in 1846, discovered not through direct observation but through mathematics, through careful analysis of Uranus's orbit that revealed it was being pulled by something unseen. Each of these discoveries reminded us that our cosmic neighborhood was larger and more complex than we had imagined. Each one required us to adjust our mental model of home, and now, in the 21st century, we might be on the verge of another such adjustment. The evidence for Planet 9 doesn't come from a single observation or a dramatic photograph. Instead, it emerges from patterns, from the peculiar clustering of distant objects in the Kuiper belt, from orbital alignments that seem too precise to be coincidental, from computer simulations that work better with a large distant planet than without one. But let's return to our first mystery, to 3i Atlas, because this is where our story really begins to take shape. Imagine, if you will, a chunk of ice and dust, no bigger than a mountain, that has been drifting in the absolute darkness beyond our solar system for billions of years. The temperature out there approaches absolute zero, so cold that even gases freeze solid. There's no light except the faint glow of distant stars, no warmth except the negligible heat left over from the object's formation. This comet, for that's what it would become, was essentially sleeping, locked in a gravitational embrace that kept it orbiting slowly in the Oort cloud, that theoretical sphere of icy bodies that surrounds our solar system like a vast invisible shell. Something disturbed it. Something gave it a gentle push, just enough to alter its orbit to send it falling toward the distant sun. We don't know what that something was, and this is where the mystery deepens. It could have been the gravitational influence of a passing star, though no known stars have passed close enough recently to account for it. It could have been the gentle tidal forces of the galaxy itself, though these are usually too weak to dislodge comets from stable orbits. Or, and this is the possibility we're exploring tonight, it could have been the gravitational influence of Planet 9, sweeping through the outer darkness like an invisible hand, disturbing the ancient peace of the Oort cloud. The journey from the Oort cloud to the inner solar system is almost impossible to imagine in human terms. If 3 Atlas began its journey when the first humans were learning to use tools, it would only now be approaching the Sun. But of course, these timescales are speculative. We can't know exactly when the comet began its fall, only that it must have been a very, very long time ago. During its journey, empires rose and fell on Earth, species evolved and went extinct, continents drifted, ice ages came and went, and all the while, this small chunk of ice and dust continued its patient approach, pulled by the Sun's gravity across billions of miles of emptiness. When we finally detected 3I Atlas in late 2019, it was already well on its way toward the Sun. Astronomers using the Atlas survey system in Hawaii spotted it as a faint point of light, moving against the background stars. At first, it seemed like it might become a spectacular comet, visible to the naked eye, perhaps even visible during daylight. Predictions suggested it could become one of the brightest comets in decades. But comets are notoriously unpredictable, and 3I Atlas had a different fate in store. As the comet approached the Sun, something beautiful and tragic happened. Instead of brightening into a spectacular display, 3I Atlas began to fragment. Through telescopes around the world, astronomers watched as the comet's nucleus broke apart, creating a trail of smaller pieces that continued along the same orbital path. It was like watching an ancient piece of pottery crumble after being exposed to sudden heat, each fragment carrying with it a piece of the original story, but no longer forming a coherent whole. The Hubble Space Telescope captured images of the disintegration, showing dozens of fragments spreading out along the comet's path, each one a tiny world unto itself, each one carrying material that had been locked in ice since the formation of our solar system. There's something profoundly moving about watching something so ancient come apart. This comet had survived for billions of years in the cold darkness, had made an incredible journey across unimaginable distances, only to dissolve just as it reached its destination. It's rather like an old letter preserved for centuries that crumbles to dust the moment someone tries to read it. The information was there, the message was real, but it was too fragile to survive the very act of observation. But even in its dissolution, 3I Atlas told us things. The way it broke apart, the composition of the gases it released, the orbit it followed, all of these provided clues about where it came from and how it got here. The orbit was particularly interesting. It was what astronomers call a near-parabolic orbit, which means the comet was moving so fast that it was barely bound to the Sun's gravity. This suggested it was likely a first-time visitor from the Oort cloud, not a periodic comet that had made this journey before. First-time visitors are special because they preserve the conditions of the early solar system, having been in deep freeze since their formation. The spectrum of light from the comet revealed the presence of various ices, water ice of course, but also carbon dioxide, carbon monoxide and other frozen gases that could only have survived in the extreme cold of the outer solar system. As these ices sublimated, turning directly from solid to gas in the warmth of the Sun, they created the comet's characteristic tail, that beautiful stream of gas and dust that always points away from the Sun, pushed by the solar wind and radiation pressure. Even as the comet died, it painted a temporary masterpiece across the inner solar system, a ghostly banner that lingered for weeks after the nucleus had completely fragmented. Now, you might wonder why astronomers were so interested in this particular comet when dozens of comets are discovered every year. The answer lies partly in its potential brightness, certainly, but also in its orbit and timing. The trajectory of 3I Atlas was unusual, approaching from a direction that aligned with some theoretical predictions about where Planet 9 might gravitationally perturb objects in the Oort cloud. This doesn't prove anything, of course. Correlation isn't causation, and a single comet's path isn't enough to confirm the existence of an unseen planet. But it adds another piece to a puzzle that astronomers have been assembling for years. The search for Planet 9 began not with a dramatic observation but with a pattern. In 2014, astronomers Chad Trucchio and Scott Shepard noticed something odd about a newly discovered object in the outer solar system. This object, along with several others in similar orbits, seemed to be clustered in a way that was statistically unlikely to occur by chance. It was as if something was shepherding them, keeping their orbits aligned like iron filings around an invisible magnet. This clustering was subtle, the kind of thing that only shows up when you look at multiple objects and analyze their orbits carefully, but it was persistent. Then, in 2016, astronomers Konstantin Batygin and Mike Brown published a paper that sent ripples through the astronomical community. They had run extensive computer simulations of the outer solar system, trying to explain the orbital clustering that Trujillo and Shepard had noticed. What they found was remarkable. The best explanation for the observed orbits was the presence of a previously unknown planet, something with about 10 times the mass of Earth, orbiting the Sun at a distance of perhaps 400 to 800 astronomical units. To put that in perspective, Neptune, our current most distant known major planet, orbits at about 30 astronomical units. Planet 9, if it exists, would be more than 10 times farther away. The evidence for Planet 9 is indirect but compelling. Beyond the clustering of distant objects, there are other anomalies that a large distant planet could explain. Some objects in the Kuiper belt have orbits that are tilted at large angles to the plane of the solar system, something that's difficult to explain without a massive perturber. The overall plane of the solar system itself seems to be tilted about 6 degrees relative to the Sun's equator, an oddity that Planet 9's gravity could account for. There are even suggestions that the hypothetical planet could explain the peculiar orbits of some objects that orbit perpendicular to the plane of the solar system. But finding Planet 9, if it exists, is extraordinarily difficult. At its predicted distance, it would be incredibly faint, perhaps 600 times dimmer than Pluto. It would be moving very slowly against the background stars, making it hard to distinguish from the countless faint galaxies and stars in deep telescope images. The search area is vast, covering hundreds of square degrees of sky. It's like looking for a single specific grain of sand on a beach, when you're not even sure which beach to search, or indeed, if the grain of sand exists at all. This is where the connection to 3i Atlas becomes intriguing. If Planet 9 exists and if it occasionally passes through or near the Oort cloud, it would inevitably disturb some of the icy bodies there, sending them falling toward the inner solar system. These disturbed comets would approach from specific directions, following paths that could be traced back to their encounter with the unseen planet. While a single comet proves nothing, a pattern of comets coming from similar directions with similar orbital characteristics could provide another line of evidence for Planet 9's existence and location. The Oort cloud itself is a theoretical construct, never directly observed but inferred from the orbits of long-period comets. Named after the Dutch astronomer Jan Oort, who proposed its existence in 1950, it's thought to be a vast spherical shell of icy bodies surrounding our solar system, at distances ranging from about 2,000 to 100,000 astronomical units from the Sun. If it exists as theorized, it contains trillions of objects, the total mass perhaps several times that of Earth, all orbiting in the slow, cold darkness at the very edge of the Sun's gravitational influence. The Oort cloud represents the absolute edge of our solar system, the boundary between what belongs to our Sun and what belongs to interstellar space. Objects in the Oort cloud are so weakly bound to the Sun that the slightest perturbation can send them on new trajectories. The gravity of passing stars, the tidal forces of the galaxy itself, and potentially the influence of Planet 9 all play a role in occasionally dislodging these ancient ice balls and sending them toward the inner solar system as comets. When we see a comet like 3i Atlas, we're looking at a time capsule from the formation of our solar system. These objects formed in the same disk of gas and dust that gave birth to the planets, but they were ejected to the outer darkness early in the solar system's history, probably by gravitational encounters with the giant planets. Out in the Oort cloud, they've been preserved in a cosmic deep freeze for billions of years, their ices and dust unchanged since the solar system was young. Each comet that falls toward the Sun brings with it information about conditions in the early solar system, chemical signatures from a time before Earth existed, before life began, before the Sun had settled into its current stable state. The fragmentation of 3I Atlas, while disappointing to those hoping for a spectacular naked-eye comet, actually provided more scientific information than an intact comet might have. As the nucleus broke apart, it exposed fresh surfaces that had never been heated by the Sun, releasing gases and dust that had been locked away for eons. Spectroscopic analysis of these releases told us about the comet's composition, the ratios of different ices, the presence of organic molecules, the size and composition of dust particles. Each fragment became a separate experiment, showing us how cometary material behaves under different conditions. There's a poetic symmetry to the idea that Planet 9, if it exists, might announce its presence not through direct observation, but through the comets it sends our way. It would be rather like deducing the presence of a person in a dark room, not by seeing them directly, but by watching the curtains move as they pass by. The comets become messengers, unconscious ambassadors from the outer darkness, their very existence and trajectories telling us about the gravitational landscape they've traversed. As we contemplate these vast scales and distant objects, it's worth remembering that everything we're discussing is happening right now, in real time, even as you listen. Somewhere in the outer darkness, comets are slowly orbiting in the Oort cloud. Planet 9, if it exists, is continuing its millennia-long orbit around the Sun. Other comets, perhaps disturbed years or centuries or millennia ago, are falling toward the inner solar system, still years away from discovery. The cosmic dance continues, patient and inexorable, whether we observe it or not. The search for Planet 9 has become one of the most intriguing quests in modern astronomy. Teams around the world are using some of the most powerful telescopes available to scan the predicted regions of sky. The Subaru telescope in Hawaii, with its enormous light-gathering power and wide field of view, has been systematically searching the most probable areas. The Dark Energy Survey, though designed for cosmological observations, has also contributed to the search. Future telescopes like the Vera Rubin Observatory will survey the entire visible sky every few nights, potentially catching Planet 9 as it slowly moves against the stellar background. But what if Planet 9 doesn't exist? What if the orbital alignments and clustering that suggest its presence are just coincidences, or the result of observational bias, or caused by something else entirely? This possibility doesn't diminish the beauty of the search. Science progresses through hypotheses tested and sometimes disproven. Even a negative result would tell us something important about our solar system, would force us to reconsider our models, and perhaps discover something even more unexpected. Some astronomers have proposed alternative explanations for the observed orbital anomalies. Perhaps instead of a single large planet, there's a disk of smaller objects whose collective gravity creates the observed effects. Maybe the clustering is temporary, a statistical fluke that will disappear as we discover more objects. Some have even suggested that a primordial black hole, captured by our solar system's gravity, could explain the observations. Each of these alternatives is being explored, tested against observations and simulations. The story of 3I Atlas and Planet 9 reminds us that we live in a solar system that still holds mysteries, that still has the capacity to surprise us. For all our sophisticated technology and centuries of observation, there are still fundamental things we don't know about our cosmic neighborhood. This isn't a failure of science, but rather a testament to the vastness and complexity of even our local corner of the universe. Every answered question reveals new questions. Every discovery opens new frontiers for exploration. As you drift deeper into relaxation, consider the profound peace of those outer realms we've been exploring. Out beyond Neptune, beyond the Kuiper Belt, in the regions where Planet 9 might roam, there is a silence more complete than anything we can experience on Earth. No wind, no sound, no vibration except the slow dance of gravity. The sun, so dominant in our sky, would appear as merely the brightest star, providing no warmth, casting shadows so faint they'd be nearly invisible. Time itself seems to slow in these regions, where a single orbit takes longer than all of recorded human history. The connection between 3i Atlas and Planet 9, whether real or imagined, speaks to something fundamental about how we understand our universe. We look for patterns, for connections, for the hidden threads that link seemingly unrelated phenomena. Sometimes these connections are real, revealing deep truths about the nature of reality. Sometimes they're coincidences that nevertheless inspire us to look closer, to ask better questions, to refine our understanding. Either way, the search itself enriches us, expands our perspective, and reminds us of our place in the cosmic order. Think about the generations of astronomers who have gazed into the outer darkness, each one adding a small piece to our understanding. From William Herschel discovering Uranus with a handmade telescope, to modern teams using supercomputers to simulate billions of years of orbital evolution, each generation builds on the work of those who came before. The search for Planet 9 and the study of comets like 3i Atlas are part of this continuum, this gradual expansion of human knowledge that stretches back to the first humans who looked up at the night sky and wondered what those lights might be. The fragmenting of 3i Atlas was observed by both professional astronomers and amateur enthusiasts around the world. In an age where so much of astronomy requires massive telescopes and sophisticated instruments, comets remain accessible to anyone with modest equipment and patience. This democratic aspect of comet observation connects us to centuries of sky watchers who have tracked these celestial visitors, recorded their appearances, and wondered about their origins. Even as we use spectroscopy and orbital mechanics to understand comets scientifically, they retain their capacity to inspire wonder, to make us feel connected to the cosmos in a direct and personal way. As we prepare to delve deeper into the specific characteristics of 3i Atlas in our next phase of exploration, let's pause for a moment to appreciate the extraordinary chain of events that had to occur for us to even know about this comet. It had to be dislodged from its stable orbit in the Oort cloud at just the right time, had to follow a path that brought it close enough to the sun to become visible, had to arrive during a period of human history when we had the technology to detect and study it. The odds against any specific comet being observed are astronomical, yet we've catalogued thousands of them, each one a messenger from the outer darkness, each one with its own story to tell. The very name 3i Atlas carries information about our system of understanding these objects. The designation tells us this was the third comet discovered in the first half of March, that it was discovered by the Atlas Survey System. This systematic naming convention, dry as it might seem, represents humanity's attempt to bring order to the cosmos, to categorize and understand the countless objects that populate our solar system. Behind every designation is a moment of discovery, often a late night at a telescope or computer screen when someone noticed something moving against the stars, something that hadn't been there before. The Atlas system itself, the Asteroid Terrestrial Impact Last Alert System, represents our latest effort to systematically survey the sky for moving objects. Though designed primarily to detect potentially hazardous asteroids, it has proven remarkably effective at discovering comets. The system consists of telescopes that photograph the same regions of sky multiple times each night, using sophisticated software to identify objects that have moved between exposures. It's a testament to human ingenuity that we can now automatically detect objects millions of miles away, track their motion, and predict their paths with extraordinary precision. When 3i Atlas was first discovered, it was about 280 million miles from the Sun, roughly the distance of the asteroid belt. At that distance, it was already beginning to warm up, its ices starting to sublimate, forming the fuzzy coma that distinguishes comets from asteroids. The initial observations suggested it was on its first journey to the inner solar system, what astronomers call a dynamically new comet. These are particularly valuable scientifically, because they preserve primordial material in a way that periodic comets, which have made multiple passes by the Sun, do not. The The excitement in the astronomical community when 3I Atlas was discovered wasn't just about its potential brightness. Every new comet is an opportunity to test our understanding of solar system dynamics, to refine our models of how these objects behave, to search for unusual characteristics that might tell us something new. The possibility that this comet might have been influenced by Planet 9 added an extra layer of interest, though most astronomers were careful not to draw premature conclusions from a single object. As 3I Atlas approached the Sun through early 2020, observers around the world tracked its progress. The comet was brightening roughly as expected, developing a green-tinted coma characteristic of diatomic carbon molecules fluorescing in sunlight. Predictions suggested it might reach magnitude 2 or brighter, easily visible to the naked eye, possibly even visible during twilight. Some optimistic predictions suggested it could become as bright as Venus, which would have made it one of the most spectacular comets in living memory. But comets, as astronomers often say, are like cats. They have tails and do exactly what they want. By late March 2020, observers began to notice that 3I Atlas wasn't brightening as rapidly as expected. The coma appeared elongated, suggesting the nucleus might be breaking apart. By early April, it was clear that the comet was disintegrating. Instead of a single bright nucleus, telescopes revealed multiple fragments, spreading out along the orbital path like pearls on a broken string. The fragmentation of a comet isn't unusual, but it is always somewhat unpredictable. Some comets survive dozens of passages near the Sun, while others, particularly dynamically new comets like 3I Atlas, fragment on their first approach. The reasons for fragmentation can vary: thermal stress from uneven heating, pressure from volatile gases escaping too rapidly, tidal forces from the Sun's gravity, or simply structural weakness in the nucleus itself. In the case of 3I Atlas, it was likely a combination of factors, with the comet's pristine, previously unheated structure unable to withstand the stresses of solar approach. The Hubble Space Telescope provided some of the most detailed images of the fragmentation, revealing about 30 separate fragments on April 20, 2020, and 25 fragments a few days later. Each fragment was surrounded by its own small coma, creating a string of miniature comets following the same orbital path. These observations provided valuable data about how comets break apart, information that helps us understand not just this specific comet, but the physical properties of cometary nuclei in general. Even as 3I Atlas disintegrated, it continued to provide scientific value. The fragmentation exposed fresh surfaces, releasing gases and dust that had been sealed inside the nucleus. Spectroscopic observations revealed the presence of various molecules, water of course, but also carbon monoxide, carbon dioxide, and more complex organic molecules. The relative abundances of these substances provided clues about where in the early solar system the comet originally formed and what conditions were like in that region billions of years ago. The dust released by the comet was also informative. As sunlight scattered off the dust particles, the patterns of polarization told astronomers about the size and composition of the grains. This dust spread along the comet's orbit will continue to orbit the Sun for years or decades, possibly creating a weak meteor shower if Earth ever passes through the debris stream. Every meteor from such a shower would be a tiny piece of 3I Atlas, a fragment of the ancient solar system burning up in our atmosphere, completing a journey that began billions of years ago in the cold darkness beyond Neptune. Now, as we transition into exploring the deeper nature of 3I Atlas and its journey, we find ourselves at the intersection of observation and speculation, where what we know meets what we can only imagine. The comet's fragmentation, rather than being an ending, becomes a beginning, a dispersal of ancient material through the inner solar system, each fragment carrying information about the deep past and possibly about the gravitational architecture of the outer solar system that sent it on its way. The story of 3I Atlas is far from unique in the annals of cometary history. Many comets have arrived with great fanfare only to disappoint observers by fragmenting or failing to brighten as expected. Comet Kohoutek in 1973 was predicted to be the comet of the century, but proved far fainter than expected. Comet Ison in 2013 was similarly hyped but disintegrated as it passed close to the Sun. Each of these failed comets, however, provided valuable scientific data and reminded us of the unpredictable nature of these ancient visitors. What makes 3i Atlas particularly intriguing in the context of our exploration is not just its individual story, but how it fits into the larger pattern of cometary arrivals. If Planet 9 exists and periodically disturbs the Oort cloud, we would expect to see comets arriving from specific directions at specific times, following a pattern that could be traced back to the gravitational influence of the unseen planet. While a single comet tells us little, the accumulated data from many comets over many years might reveal the subtle signature of Planet 9's presence. The mathematical models that predict Planet 9's orbit and mass also make predictions about its effect on the Oort cloud. Depending on its exact orbit, the planet would pass through or near different regions of the cloud at different times, creating waves of cometary disturbances that propagate inward over millions of years. These models suggest that Planet 9 might trigger comet showers, periods when the rate of long-period comets entering the inner solar system increases significantly. Some researchers have even suggested that past mass extinctions on Earth might correlate with such comet showers, though this remains highly speculative. The search for patterns in cometary arrivals is complicated by the fact that we've only been systematically discovering and tracking comets for a few centuries, a blink of an eye in cosmic terms. The historical record of bright comets goes back further, with observations recorded by Chinese, Babylonian, and other ancient astronomers, but these records are incomplete and often difficult to interpret. We're trying to discern patterns that play out over millions of years using data that spans at most a few thousand years. Modern surveys like ATLAS, along with others like Pan-STARRS and the Catalina Sky Survey, are dramatically increasing our rate of comet discovery. We now find dozens of comets each year, most too faint to see without telescopes, but each one adding to our statistical understanding of the cometary population. As our sample size grows, patterns that were previously hidden in the noise of random arrivals might become apparent, potentially revealing the influence of Planet 9 or other unknown perturbers in the outer solar system. The orbit of 3i Atlas before its fragmentation was particularly interesting from a dynamical perspective. With a period of about 6,000 years, it occupied a middle ground between short-period comets that orbit the Sun every few years or decades, and long-period comets with orbits measured in millions of years. This orbital period suggested the comet had been perturbed relatively recently, astronomically speaking, from a more distant orbit. The question is, what caused that perturbation? If we could trace 3i Atlas's orbit backward in time with perfect precision, we might be able to identify when and where it was disturbed from its original path in the Oort cloud. Unfortunately, the fragmentation of the comet introduced uncertainties into our orbital calculations, and the gravitational influences of the planets, particularly Jupiter, make it difficult to accurately reconstruct orbits over thousands of years. Still, the general characteristics of the orbit provide constraints on what could have caused the perturbation. The direction from which 3i Atlas approached is also significant. The comet came from the northern sky, from the direction of the constellation Ursa Major. This isn't the direction where most models place Planet 9, which is predicted to be in the southern sky, but the gravitational influence of a massive planet can be complex, potentially sending comets in many directions depending on the geometry of the encounter. The absence of a clear directional preference in long-period comet arrivals is actually one of the challenges in using comets to locate Planet 9. As we move forward into examining the characteristics of 3i Atlas more closely, we carry with us this sense of cosmic detective work, of piecing together clues from fragmentary evidence to understand processes that occur on scales far beyond human experience. The comet becomes not just an object of study, but a character in a larger story, a messenger whose message we're still trying to decode, a visitor whose journey connects the accessible inner solar system with the mysterious outer darkness where Planet 9 might lurk. The green colour that 3i Atlas displayed as it approached the Sun is worth contemplating for a moment. This ethereal green glow, visible in long exposure photographs, comes from diatomic carbon molecules C2, fluorescing in sunlight. These molecules form when complex carbon compounds in the comet break down under solar radiation. The green colour is almost like a signature, a sign that says, "I am a comet, I am ancient, I contain the carbon that could someday become part of living things." It's a reminder that comets may have delivered much of Earth's water and organic molecules, the raw materials from which life emerged. As the comet fragmented, each piece continued to glow with this characteristic green light, creating a procession of emerald sparks against the darkness of space. Observers with telescopes could watch this progression night after night, seeing the fragments spread out, fade, and eventually disappear. It was like watching a dandelion seed head dispersing in slow motion, each seed carrying the potential for new growth, though in this case, the seeds were chunks of ice and dust that would never coalesce again. The timing of 3i Atlas's arrival and fragmentation during the early months of 2020 meant that many observations were affected by the global situation at that time. Observatories closed or operated with reduced staff. Amateur astronomers found themselves with unexpected time to observe, and the comet became, for some, a point of focus during a period of uncertainty. There's something poetic about watching a visitor from the outer darkness during a time when humanity was grappling with its own challenges, a reminder that the universe continues its patient dance, regardless of human affairs. As we delve deeper into the nature of 3i Atlas, we begin to see it not just as a single object, but as a representative of a vast population of similar bodies. The Oort cloud, if our theories are correct, contains trillions of comets, each one a frozen time capsule from the early solar system. The few that we see, like 3i Atlas, are just the tiniest sample of this enormous reservoir. It's as if we're trying to understand an entire library by reading a few random pages that occasionally blow through our window. The chemical composition of 3i Atlas, as revealed through spectroscopy, tells us about conditions in the early solar system. The ratio of different isotopes, the presence of certain molecules, the abundance of dust versus ice, all provide clues about where and when the comet formed. These measurements suggest that 3i Atlas formed in a region where temperatures were low enough for carbon monoxide to freeze, probably beyond the orbit of Neptune, but warm enough that some processing of the primordial material had occurred. The dust released by the comet is particularly interesting because it represents solid material that has been preserved since the formation of the solar system. Unlike the ices which sublimate and are lost to space, the dust particles can potentially be collected and studied. Some of this dust will eventually fall to Earth, adding to the tons of cosmic material that rain down on our planet every day. A few grains might be collected by high-altitude aircraft or identified in Antarctic ice, where they can be studied in laboratories, revealing their mineralogy and potentially even preserving organic molecules. The fragmentation of 3i Atlas also provided an unexpected opportunity to study the internal structure of a comet. As the nucleus broke apart, it revealed that the comet wasn't a solid chunk of ice and rock, but rather a loosely bound collection of smaller pieces, what astronomers call a rubble pile. This structure, held together by weak forces and its own minimal gravity, helps explain why so many comets fragment when they approach the Sun. They're not solid objects, but more like dirty snowballs that have been gently squeezed together, ready to fall apart under stress. This rubble pile structure has implications for our understanding of Planet 9's potential influence on the Oort cloud. If comets are weakly bound collections of smaller pieces, they might be more easily disturbed by gravitational perturbations than previously thought. A close encounter with Planet 9 might not just change a comet's orbit, but could potentially break it apart, creating multiple comets from a single original body. This could amplify Planet 9's effect on the cometary population, potentially making its influence easier to detect in the statistical properties of observed comets. As we continue our journey through the story of 3I Atlas, we find ourselves moving between scales, from the microscopic dust grains released by the comet to the vast gravitational architecture of the outer solar system. Each scale reveals different aspects of the story, different clues to the mysteries we're exploring. The comet becomes a lens through which we can examine processes that span billions of years and billions of miles, connecting the formation of the solar system to the present day, the inner planets to the outer darkness. The study of 3I Atlas also highlights the international nature of modern astronomy. Observations of the comet were made by telescopes in Hawaii, Chile, Spain, Australia, and many other locations. Data was shared freely among astronomers worldwide, analysed using software developed by international collaborations, and discussed in virtual meetings that brought together experts from dozens of countries. The comet became a focal point for cooperation, a shared interest that transcended borders and boundaries. Amateur astronomers played a crucial role in monitoring 3I Atlas, providing continuous coverage that professional observatories couldn't maintain. With modest telescopes and digital cameras, amateurs around the world tracked the comet's brightness, watched for signs of fragmentation, and contributed their observations to international databases. This citizen science aspect of comet observation continues a tradition that goes back centuries, when comets were often discovered by dedicated amateurs scanning the sky night after night. The legacy of 3I Atlas extends beyond its brief appearance in our skies. The data collected during its approach and fragmentation will be analysed for years to come, contributing to our understanding of cometary physics, solar system dynamics, and potentially the existence of Planet 9. Each measurement, each photograph, each spectrum becomes part of the permanent scientific record, available for future researchers who might find patterns or connections we can't yet see. As we prepare to explore the concept of Planet 9 in greater detail, we carry with us the image of 3I Atlas, this fragile messenger from the outer darkness that briefly graced our skies before dissolving into cosmic dust. The comet serves as a tangible connection to the hypothetical world we're seeking, a possible effect of an unseen cause, a whisper that might be telling us about a shout we haven't yet heard. The journey from comet to planet, from observation to theory, from what we can see to what we can only imagine, is the journey we're about to undertake. The fragments of 3 Atlas continue their journey around the Sun, though they're now too faint for most telescopes to detect. Each piece follows essentially the same orbit as the original comet, though subtle differences in their paths will cause them to spread out over time. In thousands of years, if any of these fragments survive, they'll return to the inner solar system, perhaps to fragment again, continuing the cycle of dissolution and dispersal that gradually feeds cometary material into the inner solar system. This process of cometary dissolution is one way that material from the outer solar system is transported inward. Over billions of years, countless comets have made this journey, contributing their water and organic molecules to the inner planets. Earth's oceans might owe their existence to such cometary delivery, and the organic molecules that form the building blocks of life might have arrived the same way. In this view, comets like 3I Atlas aren't just visitors but delivery men, bringing packages from the outer darkness that, over geological time, fundamentally shape the inner solar system. The possibility that Planet 9 might be directing this delivery service adds another layer to our cosmic story. If the hypothetical planet periodically sends waves of comets toward the inner solar system, it could have played a crucial role in Earth's history, perhaps delivering the water and organics necessary for life, or perhaps occasionally triggering extinction events when too many comets arrived at once. This is highly speculative, of course, but it illustrates how the existence of Planet 9 could have implications far beyond the simple addition of another planet to our solar system's roster. As we stand at the threshold between discussing 3I Atlas and Planet 9, between the observed and the hypothetical, between the comet we watch dissolve and the planet we've never seen, we find ourselves in that twilight realm where science is most exciting. Here, at the edge of knowledge, every observation might be the key that unlocks a mystery. Every theory might be the framework that explains the unexplained. The story of 3 Atlas and Planet 9 is still being written, and we're privileged to witness its unfolding, to be part of the generation that might finally map the true extent of our solar system. The night sky continues its slow rotation as we contemplate these mysteries. Stars rise and set, planets trace their predictable paths, and somewhere in the darkness, comets continue their patient journeys. Perhaps right now, as you rest and listen, a comet disturbed by Planet 9 millions of years ago is just beginning to brighten as it feels the sun's warmth for the first time. Perhaps telescopes are capturing the first images of what will become the next great comet, or perhaps they're unknowingly photographing Planet 9 itself, its image hidden among the countless faint points of light, waiting for someone to notice that it has moved. Now, as we prepare to shift our focus from the messenger to the hypothetical sender, from 3i Atlas to Planet 9, we carry with us this sense of cosmic connection, this understanding that everything in our solar system is linked by the invisible threads of gravity, time, and shared history. The comet that dissolved before our eyes might have been sent by a planet we've never seen, a planet whose existence we infer from the dance of distant objects, from patterns in chaos, from the subtle ways that gravity shapes the architecture of our cosmic home. This is the mystery we're about to explore more deeply, the question of whether our solar system still holds major secrets, whether there's still a giant world waiting in the darkness, patiently continuing its ancient orbit while we search the sky for signs of its presence. The story of 3i Atlas reminds us that the universe rarely reveals its secrets directly. Instead, it offers us clues, fragments, and fleeting glimpses that we must carefully piece together. The comet came and went, leaving us with data to analyze, images to study, and questions to ponder. Whether it was truly connected to Planet 9 or simply another random visitor from the Oort cloud, it served its purpose as a reminder of the dynamic, ever-changing nature of our solar system, a system that still has the capacity to surprise us, to challenge our assumptions, and to expand our understanding of the cosmic neighborhood we call home. The journey we're about to take now leads us even further from the warmth of our sun, out beyond the last of the known planets, into a realm where darkness isn't just the absence of light, but seems almost like a physical presence, thick and tangible. Here, in this profound darkness, something enormous might be moving, something that has never been directly seen by human eyes, but whose gravitational signature appears to be written across the orbits of dozens of distant objects. This is the domain of the hypothetical Planet 9, a world that, if it exists, would redefine our understanding of our solar system's architecture and force us to reconsider how planetary systems form and evolve. To understand the case for Planet 9, we need to first appreciate the sheer emptiness of the outer solar system. Beyond Neptune, space doesn't just become empty, it becomes emptier than anything we can truly comprehend. If you were floating out there, the sun would appear as merely the brightest star in the sky, providing no warmth, barely any light. The darkness would be so complete that your eyes, no matter how long they adjusted, would never be able to see your own hand in front of your face without artificial light. In this darkness, objects move slowly, taking centuries or millennia to complete single orbits, following paths that have remained essentially unchanged since the solar system was young. It was in this realm that astronomers began to notice something odd about the objects they were discovering. These trans-Neptunian objects, or TNOs, chunks of ice and rock, orbiting beyond Neptune, weren't distributed randomly as you might expect. Instead, some of them seemed to be clustered, their orbits aligned in a way that suggested they were being shepherded by something massive, something that hadn't yet been detected. It was like noticing that all the boats in a harbour were pointing in the same direction, and inferring the presence of a current, even though you couldn't see the water moving. The story really begins with Sedna, discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz. Sedna was unlike anything astronomers had seen before. Its orbit took it from about 76 astronomical units from the Sun at its closest approach to nearly 940 astronomical units at its most distant point. This extreme orbit couldn't be easily explained by interactions with the known planets. Neptune, even at its most influential, couldn't have pushed Sedna into such an orbit. Something else must have been responsible. But what? As more objects with similarly extreme orbits were discovered, a pattern began to emerge. These objects, which astronomers call extreme trans-Neptunian objects or ETNOs, shared some peculiar characteristics. Their orbits were not only extremely elongated, but also clustered in their orientation. The long axes of their orbits pointed in roughly the same direction, and they all came closest to the Sun in a similar region of space. The probability of this clustering happening by chance was calculated to be less than 1%. In science, when you see a pattern that is unlikely to occur randomly, you start looking for a cause. The mathematical detective work that followed was extraordinary. Konstantin Batygin and Mike Brown, working at Caltech, spent years running computer simulations, testing different scenarios that might explain the observed clustering. They tried models with multiple small planets, models with a distant disk of material, models with passing stars. But the scenario that best matched the observations was the presence of a single large planet. Something with about 10 times the mass of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units. This hypothetical planet wouldn't just explain the clustering of the ETNOs, it would also account for other puzzling features of the outer solar system. For instance, there's a population of objects with orbits perpendicular to the plane of the solar system. These objects, orbiting almost straight up and down relative to the planets, are difficult to explain without some massive perturber. Planet 9's gravity, according to the models, would naturally create such orbits through a complex gravitational dance played out over millions of years. The proposed Planet 9 would be a remarkable world. With 10 times Earth's mass, it would be a super-Earth or a mini-Neptune, a type of planet that's actually quite common in other solar systems, but conspicuously absent from our own. It would be so distant that noon on Planet 9 would be dimmer than twilight on Earth. The Sun would appear as a point of light, brilliant but providing virtually no heat. If Planet 9 has an atmosphere, it would likely be frozen solid on the surface, creating a landscape of nitrogen or methane ice under a black sky where the stars would be visible even during the day. The orbit of Planet 9, as predicted by the models, would be extraordinary. Taking between 10,000 and 20,000 years to complete a single orbit, it would be on a highly elliptical path, perhaps coming as close as 200 astronomical units to the Sun and travelling as far as 1/200 astronomical units. This means that Planet 9 would spend most of its time in the most distant parts of its orbit, moving slowly through the darkness, which partly explains why it hasn't been detected yet. When an object is that far away and moving that slowly, it's incredibly difficult to spot against the background stars. But how could such a planet have formed so far from the Sun? The current models of solar system formation suggest that large planets can't form at such distances. There simply isn't enough material in the protoplanetary disk that far out. This has led to fascinating speculation about Planet 9's origin. Perhaps it formed closer to the Sun and was ejected to its current orbit by gravitational interactions with Jupiter or Saturn. Or maybe, and this is even more intriguing, Planet 9 isn't originally from our solar system at all. It could be a captured planet, a world that formed around another star and was stolen by our Sun during a close encounter in the early days of the solar system. The idea of our Sun stealing a planet from another star might sound like science fiction, but it's actually quite plausible given what we know about stellar nurseries. Stars don't form in isolation. They form in clusters, sometimes with thousands of stars born from the same giant molecular cloud. In these crowded stellar nurseries, close encounters between young stars would be common. If our Sun passed close to another star that had planets, the gravitational interaction could potentially transfer a planet from one star to another. Planet 9 could be an alien world, a visitor from another solar system that has been orbiting our Sun for billions of years. The search for Planet 9 has become one of the most intensive astronomical hunts of our time. The challenge is immense. At its predicted distance and brightness, Planet 9 would be about 600 times fainter than Pluto. It would be moving so slowly that distinguishing it from background stars would require observations separated by days or weeks. And the search area is vast, covering hundreds of square degrees of sky. It's often described as looking for a needle in a haystack, but it's worse than that. It's like looking for a specific needle in a field full of haystacks in the dark, when you're not even sure the needle exists. The most powerful telescopes in the world have been enlisted in the search. The Subaru telescope in Hawaii, with its enormous 8.2-meter mirror and wide-field camera, has been systematically surveying the most probable regions. Each survey image contains millions of stars and galaxies, and sophisticated software is needed to identify objects that have moved between observations. The process is painstaking, requiring careful elimination of false positives like asteroids, variable stars, and image artifacts. The predicted properties of Planet 9 place it in an interesting category. If it exists, it would be the fifth largest planet in our solar system, smaller than Neptune but larger than Earth. This size range between Earth and Neptune is actually the most common type of planet found around other stars, yet our solar system lacks any planets in this range. The discovery of Planet 9 would therefore not only add a new planet to our solar system, but would also make our planetary system more typical, more like the thousands of exoplanetary systems we've discovered. The gravitational influence of Planet 9 extends far beyond just shepherding a few distant objects. According to the models, it would affect the entire outer solar system in subtle ways. The plane of the solar system, for instance, is tilted about 6 degrees relative to the Sun's equator. This has long been a mystery, as the planets should have formed in the same plane as the Sun's rotation. Planet 9, with its tilted orbit, could provide exactly the right gravitational torque to create this misalignment over billions of years. There's something deeply humbling about the possibility that our solar system contains a major planet that we've simply missed. We've mapped the surface of Mars in exquisite detail, sent spacecraft to Pluto, and discovered thousands of planets around other stars, yet there might be a world 10 times more massive than Earth in our own backyard that has escaped detection. It reminds us that for all our technological sophistication, the universe still holds secrets, still has the capacity to surprise us. The evidence for Planet 9 isn't without controversy. Some astronomers argue that the clustering of orbits could be due to observational bias. We've only discovered a small fraction of the objects in the outer solar system, and the ones we've found might not be representative of the whole population. It's possible that when we discover more objects, the clustering will disappear, revealed as a statistical fluke rather than a real phenomenon. Others have proposed alternative explanations, such as a disk of many small objects whose collective gravity mimics that of a single large planet. These debates are healthy and necessary. Science progresses through skepticism, through rigorous testing of hypotheses, through the careful elimination of alternatives. The proponents of Planet 9 have responded to criticisms by refining their models, making more specific predictions that can be tested. For instance, they've predicted where in the sky Planet 9 should be located based on the orbits of the objects it's supposedly influencing. They've also predicted that certain types of objects with specific orbital characteristics should exist if Planet 9 is real, and several such objects have subsequently been discovered. One of the most intriguing aspects of the Planet 9 hypothesis is how it connects to our understanding of planetary system formation in general. When we look at other solar systems, we often see super-Earths or mini-Neptunes in close orbits around their stars. The traditional view was that these planets formed far from their stars and migrated inward. But what if some of them were ejected outward instead? Planet 9 might be teaching us that planetary migration is a two-way street, that the process that delivers some planets to hot, close orbits might banish others to cold, distant ones. The cultural impact of Planet 9 has been significant, even though it hasn't been confirmed to exist. It has captured the public imagination in a way that few astronomical hypotheses do. There's something romantic about the idea of a hidden planet, a dark world lurking at the edge of our solar system. It taps into our love of exploration, our desire to find new worlds, our hope that there are still major discoveries to be made. Planet 9 has become a character in our collective story about the solar system, a mysterious presence that might or might not be real. If Planet 9 exists, it would have been influencing our solar system for billions of years. Every comet it nudged from the Oort cloud, every asteroid it perturbed, every subtle change it made to the orbits of other objects would be part of its legacy. In a sense, we might have been seeing the effects of Planet 9 all along without realizing it. Some researchers have even suggested that periodic mass extinctions on Earth might correlate with Planet 9's orbit, if it periodically triggers comet showers, though this remains highly speculative. The technology to find Planet 9 is improving rapidly. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will soon begin operations. This remarkable instrument will photograph the entire visible sky every few nights, creating a movie of the cosmos that will reveal anything that moves or changes. If Planet 9 exists and is within the observatory's detection limits, it should be discovered within the first few years of operation. The anticipation in the astronomical community is palpable. But what if we don't find Planet 9? What if, after years of searching with increasingly powerful telescopes, we come up empty-handed? This wouldn't necessarily mean it doesn't exist. It might simply be fainter or more distant than predicted. But at some point, if searches continue to fail, we'll have to consider alternative explanations for the orbital clustering and other anomalies. This process of hypothesis, testing, and potential falsification is the essence of the scientific method. The psychological aspect of searching for Planet 9 is fascinating. The astronomers involved describe nights spent at telescopes or computers, scanning through images, looking for that one point of light that has moved. It's tedious work, requiring intense concentration and attention to detail. Every potential detection must be carefully verified, cross-checked against catalogues of known objects, observed again to confirm motion. The vast majority of candidates turn out to be false alarms, but the possibility that the next image might contain Planet 9 keeps researchers motivated. There's a parallel between the search for Planet 9 and the discovery of Neptune in 1846. Neptune was found through mathematical prediction, its position calculated based on perturbations in Uranus's orbit. The discovery was a triumph of mathematical astronomy, proving that Newton's laws of gravitation could be used to predict the existence of unseen worlds. Planet 9, if discovered, would be a similar triumph, but using far more sophisticated mathematics and computer modelling, dealing with much subtler effects over much greater distances. The name Planet 9 itself is provisional, a placeholder for a world that might not exist. If it's discovered, it will receive a proper name, probably from Roman or Greek mythology like the other planets. Various names have been suggested, from Proserpina to Terminus to Erebus, each carrying its own mythological weight. The naming of a new planet would be a cultural moment, a chance for humanity to collectively label a new member of our solar system family. As we contemplate Planet 9, we're really contemplating the nature of discovery itself. How do we find something we've never seen? How do we infer the presence of the invisible from the behavior of the visible? These are questions that go beyond astronomy, touching on philosophy, on the nature of knowledge, on the relationship between theory and observation. Planet 9 exists right now primarily as a mathematical construct, a solution to a set of equations, but if it's real, it's also a physical world, as real as Earth, with its own geography, weather, and perhaps even moons. The moons of Planet 9, if they exist, would be worlds unto themselves. A planet 10 times Earth's mass could potentially hold a substantial system of satellites. These moons would be even colder and darker than the planet itself, locked in eternal night, their surfaces possibly covered in exotic ices that don't exist naturally on Earth. They would orbit their planet in darkness, never experiencing anything like the day-night cycle we're familiar with, existing in a realm of perpetual twilight. The influence of Planet 9 on the Oort cloud is particularly relevant to our story. If the planet's orbit takes it through or near the cloud, it would act like a cosmic stirring rod, disturbing comets from their stable orbits and sending them toward the inner solar system. The pattern of these disturbances would depend on Planet 9's exact orbit and mass. Some models suggest that Planet 9 could trigger periodic comet showers, times when the rate of long-period comets increases dramatically. If true, this would mean Planet 9 has been periodically refreshing the inner solar system's supply of comets for billions of years. This brings us back to 3I Atlas and comets like it. Every long-period comet we observe might carry information about Planet 9's location and orbit. The direction from which comets approach, the characteristics of their orbits, the timing of their arrivals, all of these could be pieces of a vast puzzle. We're like detectives trying to reconstruct a crime scene, but the crime happened millions of years ago, and the evidence is scattered across billions of miles of space. The connection between Planet 9 and comets also raises interesting questions about the history of our solar system. If Planet 9 has been sending comets our way for billions of years, it might have played a crucial role in Earth's development. Comets are thought to have delivered much of Earth's water and organic molecules. If Planet 9 increased the rate of cometary delivery, it might have accelerated the development of conditions suitable for life. In this view, Planet 9 wouldn't just be another planet, it would be a crucial player in the story of life on Earth. The possibility that Planet 9 might be a captured world from another solar system adds another layer of complexity to this story. If true, studying Planet 9 would give us a window into conditions around another star billions of years ago. Its composition might be subtly different from the planets that formed in our solar system. It might have exotic features that don't exist on any of our native planets. It would be like having a piece of another solar system to study, a cosmic gift from a long-dead stellar sibling. As we move deeper into the mystery of Planet 9, we find ourselves grappling with fundamental questions about what we know and how we know it. The evidence for Planet 9 is indirect, based on gravitational influences rather than direct observation. This type of evidence has a long and successful history in astronomy, from the discovery of Neptune to the detection of exoplanets, through their gravitational effects on their stars. But it also requires us to have faith in our mathematical models, to believe that the patterns we see in the data are real rather than coincidental. The statistical arguments for Planet 9 are compelling but not conclusive. The clustering of orbital parameters among distant objects is unlikely to occur by chance, but unlikely things do sometimes happen randomly. The challenge is determining whether the pattern is significant enough to warrant the hypothesis of an additional planet. This is where the predictions become crucial. If Planet 9 exists, it should create specific, testable effects. Finding these predicted effects strengthens the case. Failing to find them weakens it. The computer simulations that predict Planet 9's properties are marvels of computational astronomy. They model the gravitational interactions of thousands of objects over billions of years, tracking how orbits evolve under various scenarios. These simulations require enormous computational power and sophisticated algorithms. They're like time machines, allowing us to see how the solar system might have evolved under different conditions, to test hypotheses about events that happened long before Earth existed. The fact that Planet 9, if it exists, has remained hidden for so long tells us something important about the vastness of our solar system. We tend to think of the solar system as well explored, fully mapped, but the truth is that most of it remains terra incognita. The volume of space where Planet 9 might lurk is so vast that even our best telescopes can only search a small fraction of it at a time. It's a reminder that there are still frontiers, still places where no one has looked, still opportunities for discovery. the cultural significance of finding Planet 9 would extend far beyond astronomy. It would be front-page news around the world, a reminder that we're still capable of making major discoveries about our cosmic neighborhood. It would inspire a new generation of scientists and explorers. It would appear in textbooks, requiring updates to every model of the solar system. Children would learn about 9 planets again, though the 9th would be very different from the Pluto they might have heard about from their parents. But perhaps more importantly, Planet 9 would change how we think about our place in the universe. It would show us that even our home solar system still holds major secrets. It would remind us that the universe is far stranger and more wonderful than we often assume. It would be a humbling discovery by us, revealing that we've been sharing our solar system with a massive world we didn't even know existed. The search for Planet 9 is also driving technological innovation. The techniques developed to find faint, slow-moving objects in the outer solar system have applications beyond planet hunting. They're useful for detecting potentially hazardous asteroids, for studying the Kuiper belt, for understanding the distribution of dark matter in the galaxy. The algorithms developed to process the vast amounts of data from sky surveys are pushing the boundaries of machine learning and artificial intelligence. As we contemplate the unseen shepherd that might be Planet 9, we're reminded of how much of the universe operates beyond our direct perception. Dark matter, dark energy, black holes, the interior of stars, the quantum realm. So much of reality exists in places we can't directly observe. We infer, we deduce, we build models and test predictions, slowly assembling a picture of a universe far stranger than our senses alone could reveal. Planet 9, if it exists, is part of this hidden universe, a massive world that has been invisible to us despite being part of our own solar system. The story of Planet 9 is still being written. Every observation, every non-detection, every newly discovered distant object adds another sentence to this unfolding narrative. We're living through a potential discovery in real time, watching as scientists gather evidence, refine hypotheses, and search the sky. Whether Planet 9 exists or not, the search itself is advancing our understanding of the outer solar system, revealing new objects, new patterns, new mysteries to explore. As we prepare to journey even further out, to the Oort cloud itself, we carry with us this sense of standing at the edge of discovery. Planet 9 might be out there right now, a dark world slowly orbiting in the cold, waiting to be found. Or it might not exist at all, and the patterns we see might have some other explanation we haven't thought of yet. Either way, the search continues, driven by curiosity, by the human desire to know what's out there, by the hope that our solar system still has surprises in store for us. Now, we must venture even further from home, out to the very edge of our solar system's gravitational influence, to a place that exists more in theory than in observation, a vast sphere of ice and possibility that surrounds everything we've discussed so far. The Oort cloud awaits us, a reservoir of ancient comets that might hold the key to understanding both 3i Atlas and Planet 9, a place where billions of years of solar system history lie frozen in the darkness, waiting to be awakened by a gravitational nudge from a passing star, a galactic tide, or perhaps a hidden planet. The Oort cloud is perhaps the most mysterious region of our solar system, a place we've never seen directly, but whose existence we infer from the comets that occasionally fall from it toward the sun. Imagine, if you will, a vast spherical shell surrounding our entire solar system, beginning at about 2,000 astronomical units from the sun and extending outward to perhaps 100,000 astronomical units or more. This is a distance so vast that light from the sun takes over a year to reach the outer edge of the Oort cloud. Objects there are so weakly bound to our solar system that the gravity of passing stars can be stronger than the sun's pull. To understand the scale of the Oort cloud, let's return to our basketball-sized sun analogy. If the sun were a basketball, Earth would be a peppercorn 26 yards away, and Neptune would be a coffee bean half a mile distant. The inner edge of the Oort cloud would be about 50 miles from our basketball sun, and the outer edge would be somewhere between 1,000 and 2,500 miles away. The entire cloud would be a vast sphere, thousands of miles across, with our basketball sun as a tiny point at the center. And scattered throughout this enormous volume would be trillions of icy bodies, each one a potential comet waiting for its chance to fall toward the sun. The Oort cloud is named after Jan Oort, the Dutch astronomer who proposed its existence in 1950. Oort was trying to solve a puzzle. Where do long-period comets come from? These comets, with orbital periods of thousands or millions of years, approach the sun from all directions, not just from the plane of the solar system like short-period comets. Oort realized that there must be a spherical reservoir of comets surrounding the solar system, occasionally releasing comets when disturbed by external forces. But how did the Oort cloud form? According to current theories, the objects in the Oort cloud didn't form there. Instead, they formed much closer to the sun, in the same protoplanetary disk that gave birth to the planets. These were planetesimals, small bodies of ice and rock that might have become parts of planets if circumstances had been different. But gravitational interactions with the forming giant planets, particularly Jupiter and Neptune, flung these objects outward, scattering them to the far reaches of the solar system. This scattering process was violent and chaotic. Imagine chunks of ice and rock, some as large as mountains, some as small as pebbles, being gravitationally slingshot by Jupiter's enormous mass. Most of these objects would have been ejected from the solar system entirely, flying off into interstellar space. But a small fraction, perhaps 1 in 10 or 1 in 100, ended up in bound orbits at enormous distances from the sun, forming what we now call the Oort cloud. The process took hundreds of millions of years. During this time, the early solar system was a shooting gallery, with planetesimals flying in all directions, colliding with planets and moons, and occasionally with each other. The late heavy bombardment, a period about 4 billion years ago, when the inner planets were pelted with asteroids and comets, might have been the tail end of this process, the last gasps of the solar system settling into its current configuration. Once in the Oort cloud, these objects entered a kind of cosmic hibernation. The temperature out there approaches absolute zero, about 270 degrees Celsius, or 454 degrees Fahrenheit. At these temperatures, even gases like nitrogen and methane are frozen solid. There's no weather, no erosion, no geological activity. The comets in the Oort cloud have been essentially unchanged since they arrived there billions of years ago. They're time capsules, preserving the conditions of the early solar system in pristine form. The Oort cloud is not a dense region. Despite containing trillions of objects, the distances between them are enormous. If you are floating in the Oort cloud, you might be millions of miles from the nearest comet. The chance of 2 objects colliding is essentially zero. Each comet orbits in isolation, following its own path around the distant sun, a path that might take millions of years to complete. It's the loneliest place imaginable, a vast emptiness punctuated by occasional chunks of ancient ice. The objects in the Oort cloud are so far from the sun that they're barely bound to our solar system. The sun's gravity at that distance is incredibly weak, so weak that other forces become significant. The gravity of passing stars can perturb Oort cloud comets, changing their orbits or even stealing them entirely. The Milky Way galaxy itself exerts tidal forces on the Oort cloud, a gentle but persistent pull that can, over millions of years, dislodge comets from their orbits. These perturbations are what occasionally send comets falling toward the inner solar system. A passing star might disturb a comet's orbit just enough to start it on a million-year journey toward the sun. Or the galactic tide might slowly change a comet's orbit until it becomes unstable. These processes are random and unpredictable, which is why long-period comets seem to arrive from random directions at random times. But what if there's another perturber, something within our own solar system that can disturb the Oort cloud? This is where Planet 9 enters our story again. If Planet 9 exists and if its orbit takes it through or near the inner Oort cloud, it would be a powerful source of perturbations. Unlike passing stars which affect the Oort cloud briefly and then move on, Planet 9 would be a permanent presence, continuously disturbing comets as it orbits the Sun. The effect of Planet 9 on the Oort cloud would depend on its exact orbit. If Planet 9 has a highly elliptical orbit, as predicted, it would spend most of its time in the outer parts of its orbit, possibly within the inner Oort cloud. During these periods, it would be moving slowly, maximizing its gravitational influence on nearby comets. As it moved through the cloud, it would create a wake of disturbed comets, some falling toward the Sun, others being ejected from the solar system. This process wouldn't be dramatic or sudden. Planet 9 wouldn't scatter comets like bowling pins. Instead, its influence would be subtle, a gentle gravitational nudge that slightly changes a comet's orbit. But over thousands or millions of years, these small changes would accumulate. A comet that was in a stable orbit might find its orbit becoming more elliptical, bringing it closer to the Sun on one side and farther away on the other. Eventually, the orbit might become so elliptical that the comet enters the inner solar system, becoming visible from Earth as it develops its characteristic tail. The pattern of comets sent inward by Planet 9 would carry information about the planet's orbit and mass. Computer simulations suggest that Planet 9 would create waves of comets, periods when more comets than usual enter the inner solar system. These waves would propagate inward over millions of years, eventually reaching the region where we could observe them. By analysing the timing and direction of arriving comets, we might be able to work backward to determine when and where Planet 9 disturbed them. This is incredibly complex detective work. We're trying to reconstruct events that happened millions of years ago based on observations we can make today. It's like trying to determine where a stone was thrown into a pond by studying the ripples long after they've spread across the water. The ripples are distorted by wind, by other ripples, by the shape of the pond itself. Similarly, comets disturbed by Planet 9 are also affected by the gravity of the known planets, by passing stars, by galactic tides. Untangling these various influences requires sophisticated mathematical models and extensive computer simulations. The Oort cloud might also contain clues about the early solar system that go beyond individual comets. The overall structure of the cloud, its density distribution, the orbits of its objects, all carry information about how it formed and evolved. If we could map the Oort cloud in detail, we might be able to read the history of the solar system in its structure, seeing the fingerprints of ancient events preserved in the distribution of comets. Some theories suggest that the Oort cloud might not be uniform but could have gaps, dense regions, or other structures created by the migration of the giant planets billions of years ago. If Jupiter and Saturn migrated outward early in the solar system's history, as some models suggest, they would have scattered planetesimals in specific patterns. These patterns might still be visible in the Oort cloud today, frozen in place like a photograph of the early solar system. The outer edge of the Oort cloud marks the boundary of our solar system, the place where the Sun's gravity gives way to the gravity of other stars and the galaxy itself. This boundary isn't fixed, but changes as our solar system moves through the galaxy. When we pass close to other stars, our Oort cloud and theirs might overlap, potentially exchanging comets. Over billions of years we might have captured comets from other stars, and they might have captured some of ours. This raises a fascinating possibility. Some of the comets we see might not be native to our solar system. They might be interstellar visitors, captured from the Oort clouds of other stars. These alien comets would carry information about conditions in other solar systems, potentially having different compositions or isotope ratios than native comets. Identifying such objects would be challenging but could provide unique insights into the diversity of planetary systems. The idea of exchanging material with other solar systems extends beyond just comets. If Planet 9 is indeed a captured planet from another star, it might have brought its own retinue of moons or Trojan asteroids with it. These objects would be alien artifacts in our solar system, pieces of another star's planetary system now orbiting our Sun. Studying them would be like having samples from an exoplanet without having to travel light years to get them. The Oort cloud also plays a crucial role in protecting the inner solar system. Its vast reservoir of comets acts like a buffer, absorbing perturbations that might otherwise affect the planets. When a star passes close to our solar system, it disturbs the Oort cloud first, potentially sending comets inward but also ejecting many comets entirely, reducing the cloud's mass. Over billions of years, the Oort cloud has been slowly eroding, losing mass to passing stars and galactic tides. This erosion process means the Oort cloud was probably more massive in the past. Early in the solar system's history, when the Sun was still part of its birth cluster, stellar encounters would have been much more frequent. The young Oort cloud would have been constantly disturbed, sending waves of comets toward the inner solar system. This ancient cometary bombardment might have played a crucial role in the evolution of the planets, delivering water and organic molecules to the young Earth. The connection between the Oort cloud and life on Earth is profound and multifaceted. Comets from the Oort cloud might have delivered the water that fills our oceans, and the organic molecules that became the building blocks of life. But they might also have caused mass extinctions, with large comet impacts resetting the evolutionary clock. The Oort cloud is thus both a source of life and a source of death, a cosmic reservoir that has shaped the history of our planet in ways we're only beginning to understand. The study of the Oort cloud is challenging because we can't observe it directly. The comets there are too small and too distant to see with current telescopes. We can only infer its properties from the comets that leave it and enter the inner solar system. It's like trying to understand a forest by studying the occasional leaf that blows out of it. Each comet tells us something, but the picture remains incomplete. Future missions might change this. Proposals have been made for spacecraft that would travel to the inner Oort cloud, though such missions would take decades or centuries to reach their destination. More realistically, we might be able to study the Oort cloud using next-generation telescopes capable of detecting the faint heat signatures of large objects in the cloud, or we might develop new techniques for analyzing the trajectories of incoming comets, extracting more information about their origins. The Oort cloud represents the ultimate frontier of our solar system, a place so distant and so alien that it challenges our imagination. It's a realm where our usual concepts of time and space break down, where orbits take millions of years, where the Sun is just another star, where the darkness is absolute. Yet this distant realm is connected to us, sending us visitors in the form of comets, possibly influenced by a hidden planet, definitely shaped by the history of our solar system. As we contemplate the Oort cloud, we're really contemplating the boundaries of home. Where does our solar system end and interstellar space begin? The Oort cloud suggests that this boundary is not sharp but gradual, a slow transition from the Sun's dominance to the democracy of stellar influences. We live not in an isolated system, but in a solar system embedded in a galaxy, influenced by passing stars, by spiral arms, by the cosmic environment in which we find ourselves. The possibility that Planet 9 disturbs the Oort cloud adds another layer to this cosmic interconnection. A planet we've never seen might be disturbing comets we can barely detect, sending them on journeys that take millions of years, eventually bringing them close enough to Earth that we can observe them for a few months before they disappear again into the darkness. It's a chain of cause and effect that spans enormous distances and times, connecting the invisible to the visible, the hypothetical to the observed. The Oort cloud also reminds us of the vastness of our ignorance. We've mapped the surface of Mars, we've sent probes to interstellar space, we've detected gravitational waves from colliding black holes billions of light years away, yet we know almost nothing about this vast cloud of comets that surrounds our own solar system. It's a humbling reminder that there are still profound mysteries in our own cosmic backyard, still fundamental things we don't understand about the place we call home. As we stand at the edge of the Oort cloud in our imagination, looking back toward the distant Sun, we see our solar system from a new perspective. The planets, even giant Jupiter, are invisible at this distance. The Sun is just the brightest star in a sky full of stars. We're truly at the edge, at the boundary between our solar system and the greater galaxy, and somewhere in this vast darkness, comets drift in their slow orbits, occasionally disturbed by forces seen and unseen, beginning journeys that might bring them into the light or cast them forever into interstellar darkness. The Oort cloud is more than just a reservoir of comets. It's a library of solar system history, a boundary marker of our cosmic territory, a source of both wonder and danger. It connects us to the earliest days of the solar system and to the far future when the sun will have evolved beyond recognition. It reminds us that we live in a dynamic universe where even the most stable-seeming things are slowly changing, where patient forces acting over cosmic time can create dramatic effects. Now, as we prepare to explore how Planet 9 might nudge comets from this vast reservoir, we carry with us this sense of the Oort cloud as a place of profound stillness and potential energy, a cosmic battery charged with trillions of comets, waiting for the right gravitational trigger to release them. The cloud surrounds us like a vast sphere of possibility, each comet a different future, a different story that might unfold if given the right push at the right time. The mechanism by which a massive planet might disturb this cosmic reservoir is both simple in principle and complex in practice. Gravity, that most fundamental of forces, operates according to rules we understand well, yet its effects in the Oort cloud create patterns of beautiful complexity. As we're about to discover, the gentle pull of Planet 9, if it exists, might be enough to transform sleeping comets into messengers, sending them on epic journeys from the edge of darkness to the warmth of the inner solar system, carrying with them secrets from the dawn of time and clues about the architecture of our cosmic home. In the absolute darkness of the outer solar system, where the sun provides no more light than any other star, where temperatures hover just barely above absolute zero, an ancient dance might be taking place. If Planet 9 exists, its enormous mass, 10 times that of Earth, would create a gravitational field that extends for billions of miles in all directions. This field, invisible and intangible, would nevertheless be powerful enough to alter the destinies of comets that have orbited peacefully for billions of years. The process would be slow, gentle, almost imperceptible, but given enough time, it would be inexorable. To understand how Planet 9 might nudge comets from the Oort cloud, we need to first appreciate the delicate gravitational balance that keeps these comets in their orbits. Objects in the Oort cloud are barely bound to the sun. They're like balls balanced on the edge of a hill, stable for now but requiring only the slightest push to send them rolling. The binding energy is so weak that a change in velocity of just a few meters per second, walking speed, could be enough to dramatically alter a comet's orbit. Planet 9, if it follows the orbit predicted by current models, would spend most of its time in the outer reaches of its orbit, potentially within or near the inner edge of the Oort cloud. During these periods, which might last thousands of years, the planet would be moving slowly, perhaps just a few kilometers per second. To a comet in the Oort cloud, Planet 9 wouldn't appear to zoom past, but would instead seem to drift by slowly, like a ship passing in the night, its gravitational influence felt for centuries or even millennia. The gravitational interaction between Planet 9 and a comet would follow Newton's law of universal gravitation, the same law that governs the fall of an apple and the orbit of the moon. But in the Oort cloud, this familiar force would operate on scales that challenge our intuition. The distance between Planet 9 and a comet might be millions or billions of miles, yet even at these distances, the planet's gravity would exert a measurable force, tiny but persistent, slowly changing the comet's velocity and direction. Imagine a comet in the Oort cloud, following an orbit that takes 1 million years to complete. This comet has been orbiting stably since the solar system was young, its path unchanged for billions of years. Now Planet 9 approaches, still millions of miles away but close enough that its gravity begins to matter. The comet feels a gentle pull toward the planet, a force that might be millions of times weaker than the sun's gravity, but that operates in a different direction. As Planet 9 passes, the comet's orbit changes slightly. Perhaps its speed increases by a few centimeters per second. Perhaps its direction shifts by a fraction of a degree. These changes seem negligible, but in the delicate environment of the Oort cloud, they can have profound consequences. The comet's orbit becomes more elliptical, bringing it closer to the Sun on one side and farther away on the other. If the change is large enough, the comet might find itself on a new orbit that takes it into the inner solar system. The process is statistical rather than deterministic. Planet 9 wouldn't target specific comets, but would influence all comets within a certain range. Most comets would experience only minor perturbations, their orbits changing slightly but remaining in the Oort cloud. Some would be perturbed outward, potentially being ejected from the solar system entirely, but a small fraction would be perturbed inward, beginning the long fall toward the Sun that might eventually bring them close enough to Earth to be observed. The efficiency of this process would depend on several factors: Planet 9's mass, its orbital parameters, and the structure of the Oort cloud itself. A more massive planet would influence comets at greater distances. A more elliptical orbit would bring the planet deeper into the Oort cloud, increasing the number of comets it could perturb. The density distribution of comets in the cloud would determine how many objects are available to be influenced. Computer simulations of this process reveal fascinating patterns. As Planet 9 moves through its orbit, it would create a wake of disturbed comets behind it, like a boat moving through water. This wake wouldn't be visible directly, but over millions of years it would manifest as a stream of comets entering the inner solar system from a particular direction. The timing and direction of these comets would carry information about Planet 9's orbit, like a message written in the sky. The simulations also suggest that Planet 9 wouldn't send comets inward at a constant rate. Instead, there would be pulses or waves of cometary activity, corresponding to times when the planet's orbit takes it through denser regions of the Oort cloud. These waves would take millions of years to propagate inward, eventually arriving in the observable inner solar system as periods of increased cometary activity. This pulse delivery of comets could have profound implications for the history of the solar system. If Planet 9 has been orbiting for billions of years, it would have sent multiple waves of comets toward the inner planets. Some researchers have suggested that these waves might correlate with mass extinction events on Earth, though this remains highly speculative. The idea is that periods of increased cometary flux would increase the probability of a large impact, potentially triggering ecological catastrophes. But the influence of Planet 9 on the Oort cloud wouldn't be entirely destructive. By stirring up the cloud, the planet would also refresh the supply of comets entering the inner solar system. These comets bring water and organic molecules, the building blocks of life. In a sense, Planet 9 might be a cosmic gardener, periodically watering the inner solar system with cometary material. The specific mechanism by which Planet 9 perturbs comets is worth examining in detail. When the planet approaches a comet, the gravitational interaction can be decomposed into different components. There's the direct pull toward the planet, which changes the comet's speed. There's also a tidal effect where the part of the comet closer to the planet feels a stronger force than the part farther away. For solid bodies, this tidal effect is usually negligible, but for orbits it can be significant. The geometry of the encounter matters enormously. If Planet 9 passes directly between a comet and the Sun, it might actually stabilize the comet's orbit, pulling it into a tighter bond with the solar system. But if the planet passes on the opposite side, pulling the comet away from the Sun, it might provide just enough energy to send the comet falling inward or flying outward. The outcome depends on the precise alignment of the three bodies: the Sun, Planet 9, and the comet. The concept of gravitational focusing adds another layer of complexity. Planet 9's gravity would bend the trajectories of passing comets, focusing them into certain directions like a lens focusing light. This means that comets perturbed by Planet 9 wouldn't arrive from random directions, but would show a preference for certain approach angles. This directional bias could be a signature of Planet 9's influence, distinguishable from the random arrivals expected from stellar perturbations. The timescales involved in this process are staggering. A comet disturbed by Planet 9 might take millions of years to fall from the Oort cloud to the inner solar system. During this time, the planets continue their orbits, the solar system moves through the galaxy, stars are born and die. By the time the comet arrives in our skies, the configuration of the solar system has changed completely from when it was first perturbed. This temporal disconnect makes it challenging to trace comets back to their perturbation events. The influence of Planet 9 would extend beyond just individual comets. Over billions of years, the planet would sculpt the inner edge of the Oort cloud, creating gaps where comets have been cleared out and dense regions where comets have been concentrated. This sculpting would be similar to how Jupiter shapes the asteroid belt, creating gaps known as Kirkwood gaps where orbital resonances clear out asteroids. Planet 9's gaps would be much farther out and much larger, but the principle would be the same. These structural features in the Oort cloud would be another signature of Planet 9's presence. If we could map the cloud in detail, we might see patterns that reveal the planet's orbit and mass. Unfortunately, such mapping is far beyond our current capabilities. We can only see the Oort cloud through the comets that leave it, like trying to map a forest by studying the leaves that blow away. The interaction between Planet 9 and the Oort cloud would also be influenced by external factors. When a star passes close to our solar system, it would perturb both Planet 9 and the Oort cloud. The combined effect might be complex, with the star's perturbation either amplifying or cancelling Planet 9's influence. Over billions of years, hundreds of stars have passed close enough to affect the outer solar system, each encounter adding another layer of complexity to the dynamics. Galactic tides provide another external influence. As our solar system orbits the centre of the Milky Way, it experiences tidal forces from the galaxy's mass distribution. These tides are weak but persistent, slowly changing the orbits of Oort cloud comets over millions of years. Planet 9 would also feel these tides, its orbit slowly evolving under their influence. The interplay between Planet 9's perturbations and galactic tides would create complex patterns in the flux of comets entering the inner solar system. The possibility that Planet 9 itself might have moons adds yet another layer of complexity. A massive planet could potentially capture and retain a system of satellites, especially if it migrated slowly through the outer solar system. These moons would add to the planet's gravitational influence, creating a more complex gravitational field that could perturb comets in interesting ways. Some comets might even be temporarily captured as irregular satellites of Planet 9 before being released on new trajectories. The role of resonances in this process is particularly fascinating. Orbital resonances occur when two orbiting bodies exert regular periodic gravitational influences on each other. Planet 9 might establish resonances with some Oort cloud comets, locking them into orbits that maintain a fixed relationship with the planet's orbit. These resonant comets would be protected from perturbation, creating stable islands in the otherwise chaotic dynamics of the cloud. But resonances can also be sources of instability. If a comet's orbit slowly evolves due to other perturbations, it might drift into a resonance with Planet 9. Once in resonance, the comet's orbit could change dramatically, potentially sending it toward the inner solar system or ejecting it entirely. These resonance-driven perturbations would create bursts of cometary activity at specific times in Planet 9's orbit. The temperature in the region where Planet 9 would operate is so low that even hydrogen would be frozen solid if it could accumulate. In this extreme cold, chemical reactions essentially stop, preserving comets in their primordial state. When Planet 9 nudges a comet toward the Sun, it's not just sending a chunk of ice and rock inward. It's dispatching a perfectly preserved sample of the early solar system, a time capsule that has been waiting billions of years to be opened. The comets that Planet 9 might send our way would be dynamically new, having never before entered the inner solar system. These pristine comets would be particularly valuable scientifically, as they would preserve volatile materials that are lost from comets that have made multiple passages near the Sun. The composition of these comets could tell us about conditions in the early solar system, about the chemical processes that occurred in the protoplanetary disk, about the raw materials from which planets formed. The idea that 3I Atlas might have been nudged by Planet 9 gains credibility when we consider the comet's orbital characteristics. Its near parabolic orbit suggests it was a first-time visitor from the Oort cloud. The direction from which it approached, while not perfectly aligned with Planet 9's predicted position, is not inconsistent with perturbation by the hypothetical planet, given the complex dynamics involved and the long travel time from the Oort cloud. The fragmentation of 3I Atlas as it approached the Sun might also be related to its perturbation history. If the comet was disturbed by Planet 9, it might have experienced tidal stresses that created fractures or weak points in its structure. These pre-existing weaknesses might have made the comet more susceptible to fragmentation when exposed to solar heating. In this view, the comet's dissolution wasn't just a random event but a consequence of its encounter with Planet 9 millions of years ago. As we consider the mechanism by which Planet 9 might influence comets, we're really exploring the fundamental ways that gravity shapes our solar system. Every object, from the smallest dust grain to the largest planet, exerts gravitational influence on every other object. Usually these influences are too small to matter, overwhelmed by the dominant gravity of the Sun or nearby planets. But in the Oort cloud, where the Sun's grip is weak and distances are vast, even small perturbations can have dramatic effects. The search for Planet 9 through its cometary calling cards is an exercise in patience and statistics. We need to observe many comets, carefully measure their orbits, and look for patterns that might reveal the planet's influence. Each comet provides only a tiny piece of information, a single data point in a vast parameter space. But as our sample grows, patterns might emerge, subtle correlations that point toward the gravitational influence of an unseen world. The possibility that Planet 9 has been sending us comets for billions of years raises profound questions about the role of chance in the history of our solar system. If a comet nudged by Planet 9 delivered the water that fills our oceans, then the existence of life on Earth might depend on the orbit of a planet we've never seen. If a comet impact triggered the extinction of the dinosaurs, clearing the way for mammals to dominate, then human existence might be contingent on Planet 9's gravitational influence. These connections between the distant and the immediate, between the invisible and the consequential, remind us that we live in an interconnected cosmos where everything influences everything else. Planet 9, if it exists, isn't just a distant world orbiting in darkness. It's an active participant in the ongoing evolution of our solar system, a cosmic puppeteer pulling gravitational strings that extend across billions of miles and millions of years. As we contemplate the nudge from the giant, we're really contemplating the nature of causation in complex systems. In a chaotic system like the solar system, small changes can have large effects, and effects can be separated from their causes by enormous gaps in space and time. Planet 9's gentle gravitational nudge, barely perceptible in human terms, might be enough to send a comet on a journey that ends with a spectacular display in Earth's skies, or more dramatically, with an impact that changes the course of evolution. The beauty of this mechanism lies in its simplicity and inevitability. If Planet 9 exists, it must perturb comets. It has no choice. Gravity allows no exceptions, and if comets are perturbed, some must fall toward the Sun. Orbital dynamics demands it. This chain of necessity, from planet to comet to inner solar system, creates a link between the seen and unseen, the known and unknown. It's a link we can study, measure, and use to probe the mysteries of our cosmic neighborhood. As we prepare to follow the ghostly trail of evidence that might connect 3 Atlas to Planet 9, we carry with us this understanding of the mechanism that might link them. We see how a planet orbiting in darkness could reach out across billions of miles to nudge a sleeping comet, sending it on an epic journey that would end with its dissolution in the inner solar system. Observed by astronomers on a small blue planet who would wonder about its origins and what its arrival might mean, The trail we're about to follow is faint and circumstantial, marked more by possibilities than certainties. But in the realm of planetary astronomy, where direct observation is often impossible, and inference is our primary tool, such ghostly trails are often all we have. Like detectives working a cold case, we must examine every piece of evidence, consider every possibility, and slowly build a picture of what might have happened in the darkness at the edge of our solar system millions of years ago. When a hypothetical planet might have given a gentle push to an ancient comet, setting in motion a chain of events that would culminate with humanity glimpsing for just a moment a messenger from the cosmic frontier. The trail that connects 3i Atlas to Planet 9 is written not in stone but in mathematics, in the subtle language of orbital mechanics that describes how objects move through space under the influence of gravity. To follow this trail, we must become cosmic detectives, examining the evidence left behind by a comet that no longer exists as a single entity, searching for clues that might tell us whether its journey began with a nudge from an unseen planet or from some other cosmic influence. The path we're following is ghostly indeed, marked by measurements that carry uncertainties, by models that make assumptions, by correlations that might be coincidences. Yet it's precisely this kind of detective work that has led to many of astronomy's greatest discoveries, from the existence of Neptune to the expansion of the universe. When 3 Atlas was first discovered in December 2019, it appeared as nothing more than a faint smudge in the images captured by the Atlas survey telescopes in Hawaii. The initial observations revealed an object moving against the background stars, following a path that would bring it close to the Sun in May 2020. The preliminary orbital calculations suggested something interesting. This was likely a long-period comet, possibly on its first journey to the inner solar system from the Oort cloud. These dynamically new comets are particularly valuable because they preserve primordial material in a way that periodic comets, heated repeatedly by the Sun, do not. The orbit of 3i Atlas was hyperbolic, or very nearly so, which means the comet was moving fast enough that it was barely bound to the Sun's gravity. This is characteristic of comets from the Oort cloud, which orbit so far from the Sun that they're easily perturbed by external forces. The specific parameters of the orbit, what astronomers call the orbital elements, provided clues about where the comet came from and what might have sent it on its journey. The inclination of the orbit, about 45 degrees to the plane of the solar system, suggested the comet came from well above the ecliptic plane. The direction of approach, from the constellation Ursa Major in the northern sky, provided another piece of the puzzle. To understand whether Planet 9 might have been responsible for sending 3i Atlas toward the Sun, astronomers needed to work backward, tracing the comet's path into the past. This process, called orbital backtracking or backward integration, uses computer models to reverse the effects of gravity, essentially running time backward to see where the comet was millions of years ago. It's like watching a movie in reverse, seeing the comet rise from the Sun back to the Oort cloud, trying to determine what set it in motion in the first place. This backward integration is complicated by several factors. First, the fragmentation of 3i Atlas introduced uncertainties into the orbital measurements. When a comet breaks apart, the fragments can have slightly different velocities due to the forces involved in the fragmentation. This makes it difficult to determine the exact orbit of the original intact comet. Second, the gravitational influences of the planets, particularly Jupiter, significantly affect the comet's path. Over millions of years, these planetary perturbations accumulate, making it increasingly uncertain where the comet was in the distant past. Despite these challenges, astronomers were able to establish some constraints on 3i Atlas's history. The comet's orbital period, before it was perturbed into its Sun-approaching orbit, was probably around 6,000 years. This relatively short period for an Oort cloud comet suggests it came from the inner edge of the cloud, perhaps 2,000 to 5,000 astronomical units from the Sun. This is interesting because it's exactly the region where Planet 9, if it exists, would have its greatest influence on Oort cloud comets. The timing of 3I Atlas's arrival is another piece of evidence to consider. If Planet 9 has an orbital period of 10,000 to 20,000 years, as models suggest, it would create waves of cometary activity with similar periods. The arrival of 3I Atlas could be part of such a wave, though proving this would require identifying other comets with similar orbital characteristics arriving around the same time. This is challenging because most comets are discovered only when they are already approaching the Sun, making it difficult to determine if they're part of a coordinated wave or random arrivals. The direction from which 3I Atlas approached provides another clue, though an ambiguous one. Current models place Planet 9 in the southern sky, in the constellation Cetus or Eridanus, roughly opposite to where 3I Atlas originated. At first glance, this might seem to rule out Planet 9 as the perturber. However, the dynamics of cometary perturbation are complex. Depending on the geometry of the encounter, Planet 9 could send comets in many different directions, not just directly away from its position. Moreover, the millions of years it takes for a comet to fall from the Oort cloud to the inner solar system means that both Planet 9 and the solar system's orientation have changed significantly since the perturbation occurred. Computer simulations of Planet 9's effect on the Oort cloud provide a framework for interpreting 3I Atlas's orbit. These simulations, run on supercomputers, model the gravitational interactions between Planet 9, the Sun, and millions of test particles representing Oort cloud comets. The simulations track how these particles evolve over billions of years, recording which ones are sent toward the inner solar system and what their orbital characteristics would be. The results of these simulations are statistical rather than deterministic. They don't predict that specific comets will arrive at specific times, but rather give probabilities for different types of events. According to the simulations, if Planet 9 exists, we should see an enhancement in the flux of long-period comets with certain orbital characteristics. The orbit of 3I Atlas falls within the range of possibilities, though it's not a smoking gun. It's consistent with perturbation by Planet 9, but also consistent with perturbation by other mechanisms. One particularly intriguing aspect of 3I Atlas's orbit is its argument of perihelion, the angle that describes where the comet comes closest to the Sun relative to its orbital plane. This parameter, combined with the longitude of the ascending node, describes the three-dimensional orientation of the orbit. For objects perturbed by Planet 9, models predict a clustering of these angles, similar to the clustering seen in the orbits of extreme trans-Neptunian objects. The orbital angles of 3I Atlas are marginally consistent with this prediction, though the uncertainties are large. The chemical composition of 3I Atlas, as revealed through spectroscopy before its fragmentation, provides additional context. The comet showed strong emissions from diatomic carbon, C2, giving it a characteristic green color, as well as emissions from cyanogen, Cn, and other molecules. The relative abundances of these molecules suggested the comet formed in a region where temperatures were extremely low, consistent with an origin in the Oort cloud. The detection of carbon monoxide, which sublimates at very low temperatures, indicated the comet had been preserved in extreme cold for billions of years. The fragmentation of 3I Atlas itself might carry information about its perturbation history. Some researchers have suggested that tidal stresses during a close encounter with Planet 9 could create fractures or weak points in a comet's structure. These pre-existing weaknesses might make the comet more likely to fragment when heated by the Sun. The fact that 3I Atlas fragmented relatively far from the Sun before reaching the intense heating zone where many comets break apart could be interpreted as evidence for pre-existing structural damage. The dust released during 3I Atlas's fragmentation has been studied extensively. The size distribution of dust particles measured through their light scattering properties suggested the comet contained a mixture of fine dust and larger grains. This heterogeneous structure is consistent with a primordial object that formed through gentle accretion in the early solar system. The dust tail's evolution over time, tracked by telescopes worldwide, provided information about the range of particle sizes and their ejection velocities. Comparing 3I Atlas to other long-period comets provides context for evaluating its possible connection to Planet 9. Over the past century, astronomers have observed hundreds of long-period comets, building up a statistical picture of their orbital characteristics. Most arrive from random directions with a variety of orbital inclinations and eccentricities. If Planet 9 is influencing the flux of comets, we would expect to see subtle deviations from this random distribution, perhaps a slight excess of comets from certain directions or with certain orbital characteristics. The search for such patterns is complicated by observational biases. We're more likely to discover comets that pass close to Earth, that approach from certain directions, or that become particularly bright. These selection effects must be carefully accounted for when looking for the signature of Planet 9 in the cometary population. It's like trying to determine if a dice is loaded when you can only see some of the rolls and don't know which ones you're missing. The role of other potential perturbers must also be considered. Passing stars, the galactic tide, and even undiscovered objects in the outer solar system could all send comets toward the Sun. Each mechanism would leave its own signature in the orbital distribution of arriving comets. Distinguishing between these different signatures requires large samples and sophisticated statistical analysis. The case of 3I Atlas alone cannot prove or disprove the influence of Planet 9. It can only add one more data point to the growing collection. The trajectory of 3I Atlas after its discovery provides information about the forces acting on it in the inner solar system. As the comet approached the Sun, its path was influenced not just by gravity but also by non-gravitational forces. The sublimation of ices creates jets of gas that act like tiny rockets, pushing the comet in various directions. These forces, while small, accumulate over time and must be modelled to accurately determine the comet's original orbit. For 3 Atlas, the fragmentation complicated this modelling, as each fragment experienced different non-gravitational forces. The international effort to observe 3I Atlas created a rich dataset that continues to be analysed. Telescopes in space and on the ground, professional observatories and amateur astronomers all contributed observations. The Hubble Space Telescope provided high-resolution images of the fragmentation. The Solar and Heliospheric Observatory, SOHO, tracked the comet as it approached the Sun. Ground-based spectroscopy revealed the comet's changing composition as different ices sublimated. This collaborative effort exemplifies modern astronomy, where global cooperation enables comprehensive study of transient phenomena. The possibility that 3I Atlas was influenced by Planet 9 has implications for future comet observations. If Planet 9 exists and is actively perturbing comets, we should expect to see more comets with similar characteristics arriving in the coming years and decades. These future comets would provide additional tests of the hypothesis. If they show the predicted clustering of orbital parameters, it would strengthen the case for Planet 9. If they don't, it might suggest that 3I Atlas's orbit was coincidental rather than indicative of a hidden planet's influence. The ghostly trail we're following extends beyond just orbital dynamics. The isotopic composition of comets can provide information about where they formed and what they've experienced. Different regions of the early solar system had different isotopic ratios, fingerprints that are preserved in comets. If we could measure the isotopic composition of comets perturbed by Planet 9 and compare them to comets perturbed by other mechanisms, we might find systematic differences. Unfortunately, such measurements require either sample return missions or extremely high-resolution spectroscopy, both of which are challenging for faint, distant comets. The connection between 3I Atlas and Planet 9 also raises questions about the comet's ultimate fate. After fragmenting, the pieces of 3I Atlas continued on similar orbits, gradually spreading out due to slightly different velocities. Most of these fragments have likely sublimated completely or become too faint to detect. However, some of the dust and possibly some small fragments remain in orbit around the Sun. In thousands of years, Earth might pass through this debris stream, creating a minor meteor shower, a delayed echo of the comet's dissolution. The scientific value of 3i Atlas extends beyond its potential connection to Planet 9. Every comet we observe adds to our understanding of the solar system's formation and evolution. The composition of 3i Atlas told us about the conditions in the region where it formed. Its structure revealed information about how planetesimals assembled in the early solar system. Its fragmentation provided data on the strength and composition of cometary nuclei. Even if 3i Atlas had nothing to do with Planet 9, it was a valuable scientific opportunity. The human dimension of following this ghostly trail is worth considering. Around the world, astronomers spent countless hours observing 3i Atlas, analyzing data, running simulations, and debating interpretations. Graduate students wrote theses on aspects of the comet's behavior. Amateur astronomers stayed up all night to capture images. Science communicators explained the comet's significance to the public. This collective effort focused on understanding a chunk of ice and dust that no longer exists as a coherent object, exemplifies humanity's curiosity about our cosmic environment. The uncertainty inherent in connecting 3i Atlas to Planet 9 is actually typical of cutting-edge astronomy, and we rarely have definitive proof of our theories, especially when dealing with objects at the edge of detectability or events that occurred millions of years ago. Instead, we build cases based on accumulating evidence, statistical arguments, and the elimination of alternatives. The possible connection between 3i Atlas and Planet 9 is one piece of a larger puzzle, a single thread in a tapestry we're still weaving. As we examine this ghostly trail, we're reminded that absence of evidence is not evidence of absence. The fact that we cannot definitively link 3i Atlas to Planet 9 doesn't mean the connection doesn't exist. It might simply mean we don't yet have enough information, that our models aren't sophisticated enough, or that we're not looking at the problem from the right angle. Science often advances through patient accumulation of data, with breakthrough insights coming only after years or decades of careful observation. The technological advances that enabled the discovery and study of 3i Atlas are remarkable. The Atlas system that discovered the comet uses sophisticated software to automatically detect moving objects in telescope images. This software can process thousands of images per night, identifying potential comets and asteroids that would be impossible for humans to find manually. The spectroscopic techniques used to analyze the comet's composition can detect molecules present in trace amounts, revealing subtle details about the comet's chemistry. The orbital computation methods can integrate the motion of objects over millions of years, accounting for the gravitational influences of multiple bodies. Looking forward, the ghostly trail of 3i Atlas might become clearer as we discover more similar objects. Each new long-period comet provides another data point, another opportunity to test the Planet 9 hypothesis. Statistical patterns that are invisible with small samples might become obvious with larger ones. The Vera Rubin Observatory, with its ability to survey the entire visible sky every few nights, will dramatically increase our rate of comet discovery. Within a decade, we might have a sample large enough to definitively test whether Planet 9 is influencing the flux of long-period comets. The philosophical implications of this ghostly trail are profound. We're attempting to understand events that occurred millions of years ago in regions of space we've never visited, involving objects we can barely see. We're using the present to reconstruct the past, using the visible to infer the invisible. This is the essence of astronomical research, where direct experimentation is usually impossible, and we must rely on observation, theory, and inference to understand the cosmos. The story of 3i Atlas and its potential connection to Planet 9 also illustrates the interconnected nature of astronomical research. Understanding this one comet requires knowledge from multiple fields: orbital dynamics, cometary physics, solar system formation, stellar evolution, galactic dynamics, and more. No single person can be an expert in all these areas, making collaboration essential. The ghostly trail we're following is being mapped by a global community of scientists, each contributing their expertise to the larger picture. as we prepare to explore alternative explanations for 3i Atlas's journey, we carry with us the recognition that the ghostly trail we've been following might lead nowhere, or it might lead to a discovery that transforms our understanding of the solar system. The evidence is suggestive but not conclusive, intriguing but not definitive. This is often how science operates at the frontier of the knowledge, in the twilight zone between the known and unknown, where every observation might be the key that unlocks a mystery or just another piece of an incomplete puzzle. The trail from 3i Atlas to Planet 9 is indeed ghostly, marked more by possibilities than certainties, by what might be rather than what definitely is. Yet it's precisely these uncertain trails that often lead to the most profound discoveries. The history of astronomy is full of examples where following tenuous connections and unlikely possibilities led to revolutionary insights. Perhaps 3i Atlas will be remembered as one of the first messengers from Planet 9, or perhaps it will be remembered simply as a beautiful comet that briefly graced our skies before dissolving into cosmic dust. Either way, the search for connections, the following of ghostly trails, continues, driven by our fundamental desire to understand our place in the cosmos. Now, as we turn to consider other possible explanations for 3i Atlas's journey, we must hold multiple possibilities in our minds simultaneously. The universe rarely offers simple, unambiguous answers to our questions. Instead, it presents us with puzzles that have multiple possible solutions, each with its own implications and consequences. The art of astronomy lies not just in finding answers, but in knowing which questions to ask and being comfortable with uncertainty as we search for truth in the darkness. The cosmos is vast and full of forces that can nudge a comet from its ancient orbit, sending it on a journey toward the sun. While Planet 9 presents an intriguing possibility for explaining 3i Atlas's arrival, it is far from the only mechanism that could have set this cosmic snowball in motion. The universe operates on scales of time and space that dwarf human experience, where stellar encounters that seem impossibly rare to us are actually common over billions of years, where the gentle pull of the galaxy itself can slowly reshape orbits, where chaos and chance play roles as important as any deterministic force. To truly understand 3i Atlas's journey, we must consider all these possibilities with equal care, examining each potential cause with the same scientific rigor, remaining open to the possibility that the true explanation might be something we haven't yet imagined. The most traditional explanation for long-period comets like 3i Atlas is perturbation by passing stars. Our Sun, like all stars, is in constant motion through the galaxy, orbiting the galactic center at about 230 kilometers per second. This motion carries us through regions of varying stellar density, sometimes through relatively empty space, sometimes through regions where stars are more closely packed. Over the 4.6 billion years of our solar system's existence, thousands of stars have passed close enough to gravitationally influence the Oort cloud. These stellar encounters don't need to be dramatically close to have significant effects. A star passing within a light year of the Sun, while still tens of thousands of times farther away than Pluto, can perturb millions of comets in the Oort cloud. The effect is statistical rather than targeted. The passing star doesn't aim at specific comets, but influences all comets within a certain range, sending some inward, some outward, and leaving others relatively unaffected. It's like a cosmic lottery where the passing star draws the winning numbers, determining which comets begin their long fall toward the Sun. The most recent close stellar encounter that we know about occurred about 70,000 years ago, when Schultz's star, a binary system consisting of a red dwarf and a brown dwarf, passed through the outer Oort cloud at a distance of about 0.8 light years. This encounter was discovered through careful analysis of the star's motion, backtracking its path to determine when and how close it approached our solar system. While 70,000 years might seem like ancient history to humans, it's recent in astronomical terms, and comets perturbed by this encounter could still be arriving in the inner solar system, Looking forward, we can predict future stellar encounters with reasonable accuracy. The star Gliese 710 is currently heading almost directly toward our solar system and will pass within about 0.16 light-years in approximately 1.3 million years. This will be one of the closest stellar encounters in our solar system's history, close enough to significantly perturb the Oort cloud and potentially send a shower of comets toward the inner planets. The effects of this encounter will last for millions of years, a prolonged period of increased cometary activity that future Earth inhabitants, human or otherwise, will have to contend with. But we don't need to wait for future encounters to see the effects of stellar perturbations. Statistical analysis of long-period comet orbits suggests that many of them were likely perturbed by stars we haven't identified, stars that passed by millions of years ago and have since moved far away. The challenge is that over such long timescales, the motion of stars becomes increasingly uncertain. We can track stellar positions back a few million years with reasonable accuracy, but beyond that, the uncertainties grow exponentially. The passing star that sent 3I Atlas on its journey might now be hundreds of light-years away, impossible to identify with certainty. The galactic tide presents another mechanism for perturbing Oort cloud comets. As our solar system orbits the galactic center, it experiences tidal forces from the galaxy's mass distribution. These forces are incredibly weak at the scale of the inner solar system, completely negligible for planets and asteroids. But in the Oort cloud, where objects are barely bound to the sun, galactic tides can be significant. They work slowly but persistently, gradually changing cometary orbits over millions of years. The galactic tide doesn't act uniformly on the Oort cloud. Because the galaxy is disc-shaped rather than spherical, the tidal forces are stronger in some directions than others. This creates a pattern in the arrival directions of long-period comets, with more comets coming from certain regions of the sky. This pattern has been observed and matches theoretical predictions, confirming that galactic tides do indeed influence cometary orbits. The question is whether 3I Atlas's orbit is consistent with perturbation by galactic tides alone, or whether additional mechanisms are needed. The vertical oscillation of our solar system through the galactic disk adds another layer of complexity. The Sun doesn't orbit the galactic center in a flat circle, but oscillates up and down through the disk with a period of about 60 million years. When we pass through the dense midplane of the disk, we encounter more stars, more molecular clouds, and stronger gravitational perturbations. Some researchers have suggested that these passages through the galactic plane correlate with periods of increased cometary activity, and possibly with mass extinction events on Earth, though this remains controversial. Giant molecular clouds represent another potential perturber of Oort cloud comets. These vast clouds of gas and dust where new stars are born can be hundreds of light-years across and contain millions of solar masses. When our solar system passes near or through such a cloud, the gravitational effects can be substantial. The cloud's gravity can perturb comets directly, and the increased density of stars near star-forming regions means more stellar encounters. Additionally, the gas and dust in the cloud could have direct physical effects on the outer solar system, though these would be extremely subtle. The possibility of undiscovered objects in the outer solar system beyond Planet 9 must also be considered. There could be large asteroids, dwarf planets, or even brown dwarfs lurking in the darkness that we haven't detected yet. Each of these would have its own gravitational influence, potentially perturbing comets in ways we haven't accounted for. The discovery of Sedna, Eris, Makemake, and other large trans-Neptunian objects over the past 2 decades shows that our census of the outer solar system is far from complete. Some researchers have proposed that instead of a single Planet 9, there might be multiple smaller planets in the outer solar system. This oligarchy model suggests that several Mars or Earth-sized planets could collectively produce the orbital alignments we observe in extreme trans-Neptunian objects. If true, these multiple planets would also influence Oort cloud comets, potentially in complex ways that would be difficult to distinguish from the influence of a single larger planet. The orbital characteristics of 3I Atlas don't definitively favour one model over the other. The role of the Nice model in explaining 3I Atlas's origin deserves consideration. The Nice model, named after the French city where it was developed, proposes that the giant planets migrated significantly early in the solar system's history. According to this model, Jupiter migrated slightly inward while Saturn, Uranus and Neptune migrated outward, with Neptune potentially doubling its distance from the Sun. This migration would have scattered countless planetesimals into the Oort cloud, and the orbital characteristics of these scattered objects might differ from those of objects that formed in place. If 3I Atlas was scattered into the Oort cloud during this early migration, its composition and structure might carry signatures of its origin in the warmer inner solar system. The detection of certain molecules or isotope ratios could potentially distinguish between comets that formed in different regions. Unfortunately, the fragmentation of 3I Atlas before detailed spectroscopic analysis could be performed means we'll never know its full compositional story. Chaos theory plays a crucial role in understanding cometary dynamics. The three-body problem, the motion of three objects under mutual gravitational attraction, has no general analytical solution and can exhibit chaotic behavior. In the context of 3I Atlas, this means that tiny differences in initial conditions or small perturbations from multiple sources could lead to dramatically different outcomes. A comet that might have remained in the Oort cloud for billions more years could be sent sunward by an accumulation of tiny nudges, no single one of which would have been sufficient alone. This chaotic sensitivity makes it nearly impossible to definitively determine what perturbed a specific comet. Even if we knew the exact current orbit of 3I Atlas, which we don't due to its fragmentation, and even if we could perfectly model all gravitational influences, which we can't, the exponential growth of uncertainties when integrating orbits backward over millions of years would prevent us from identifying the specific cause of perturbation. We're left with probabilities rather than certainties, with multiple scenarios that could explain the observed orbit. The interstellar origin hypothesis, while unlikely for 3I Atlas, deserves mention. The discoveries of Oumuamua and Borisov, the first confirmed interstellar objects to pass through our solar system, have shown that objects from other star systems do occasionally visit us. While 3I Atlas's orbit was consistent with an origin in our own Oort cloud rather than interstellar space, the possibility that some comets we observe might be interstellar visitors adds another layer of complexity to interpreting cometary origins. If some fraction of apparent Oort cloud comets are actually interstellar objects, it would affect our statistical analyses of cometary populations. We might be mixing two different populations with different origins and characteristics, making it harder to identify patterns that could reveal Planet 9's influence. Distinguishing between Oort cloud comets and interstellar interlopers requires precise orbital determinations and, ideally, compositional analysis that could reveal non-solar isotope ratios or molecular abundances. The role of non-gravitational forces in shaping 3I Atlas's journey must also be considered. While gravity dominates the motion of comets over long timescales, other forces can be significant. The Yarkovsky effect, where thermal radiation from a rotating body creates a small thrust, can alter orbits over millions of years. For comets, outgassing creates jet forces that can significantly change trajectories. Electromagnetic forces from the solar wind and the sun's magnetic field can influence charged dust particles. While these forces are typically small for Oort cloud comets far from the sun, their cumulative effect over millions of years could be significant. The fragmentation of 3I Atlas itself raises questions about what caused the comet to break apart. Was it simply thermal stress from solar heating, or were there pre-existing weaknesses in the comet's structure? If the comet had a close encounter with a massive object millions of years ago, tidal stresses might have created fractures that remained dormant until solar heating caused them to propagate. Alternatively, the comet might have collided with another object in the Oort cloud, creating damage that only became apparent when the comet warmed up near the sun. The possibility of comet showers adds another dimension to our consideration of 3I Atlas's origin. Various mechanisms could trigger periods of increased cometary flux from the Oort cloud. A particularly close stellar passage, the Sun's passage through a dense region of the galaxy, or the perturbation effects of Planet 9 could all cause temporary increases in the rate of comet arrivals. If 3I Atlas was part of such a shower, we would expect to see other similar comets arriving around the same time. The challenge is that comet showers can last millions of years, making it difficult to identify them in our limited observational record. The anthropic principle offers a philosophical perspective on 3I Atlas's arrival. We observe this comet because we happen to exist at a time when it passed through the inner solar system. There might have been countless similar comets over Earth's history that arrived when no one was around to observe them. Our detection of 3I Atlas is thus partly a matter of cosmic coincidence, a chance alignment of the comet's million-year journey with humanity's brief moment of astronomical capability. Solar system analogues around other stars provide context for understanding our own system's cometary population. Observations of debris disks around other stars, detections of exocomets transiting their host stars, and theoretical models of planetary system evolution all suggest that Oort cloud-like structures might be common. If so, the processes that sent 3I Atlas toward our Sun might be universal, operating in countless systems throughout the galaxy. Understanding these processes in our own system helps us understand planetary systems in general. The role of resonances in the outer solar system could have influenced 3I Atlas's perturbation. Mean motion resonances, where orbital periods form simple integer ratios, can create regions of stability or instability. If 3I Atlas's original orbit was near a resonance with a massive perturber, whether Planet 9, Neptune, or something else, small perturbations could have been amplified over time, eventually sending the comet sunward. Identifying these resonances requires detailed dynamical modeling and consideration of multiple perturbing bodies. As we consider all these alternative explanations for 3I Atlas's journey, we're reminded of the complexity of the solar system. Multiple mechanisms operate simultaneously, each contributing to the overall dynamics. Stellar passages perturb comets, while galactic tides slowly reshape orbits, while planetary perturbations add their own influences. Untangling these various effects to identify the dominant mechanism for any particular comet is a formidable challenge. The scientific method requires us to consider all plausible hypotheses and test them against available evidence. For 3I Atlas, the evidence is limited. We have its orbit, with uncertainties due to fragmentation, its basic composition, and its behavior as it approached the Sun. This isn't enough to definitively identify what perturbed it from the Oort cloud. We can say that its characteristics are consistent with several mechanisms, including perturbation by Planet 9, but we cannot prove which mechanism was responsible. The beauty of this uncertainty is that it drives further research. Each new comet we discover, each refinement of our models, each improvement in our observational capabilities brings us closer to understanding the full picture. The mystery of 3I Atlas's origin isn't a failure of science, but an invitation to deeper investigation. It reminds us that even in our own solar system, there are still fundamental processes we don't fully understand, still questions that challenge our best theories. Looking forward, the next generation of telescopes and surveys will dramatically improve our ability to test these various hypotheses. The Vera Rubin Observatory will discover far more comets, building up the statistical sample needed to identify subtle patterns. The James Webb Space Telescope can perform detailed spectroscopic analysis of comets, potentially identifying compositional signatures that reveal their origins. Future space missions might even visit Oort cloud comets directly, though such missions would take decades or centuries to reach their targets. The story of 3I Atlas thus becomes not just about one comet, but about our evolving understanding of the solar system. Each possible explanation for its journey teaches us something different. If stellar perturbation was responsible, It reminds us of our solar system's interaction with its galactic environment. If galactic tides were the cause, it highlights the influence of large-scale structures on small objects. If Planet 9 was involved, it points to major components of our solar system we haven't yet discovered. And if multiple mechanisms contributed, it underscores the complex, interconnected nature of celestial mechanics. As we prepare to contemplate what it would mean if Planet 9 exists, we carry with us this appreciation for the multiple forces that shape our solar system. The journey of 3I Atlas from the Oort cloud to its dissolution near the Sun could have been triggered by any number of mechanisms, each operating on different timescales, each leaving subtle signatures in the comet's orbit and composition. The fact that we cannot definitively identify the cause doesn't diminish the wonder of the journey itself, the epic voyage of an ancient chunk of ice across billions of miles and millions of years to briefly grace our skies before returning to dust. The whispers in the dark that we've been listening to, the faint signals from passing stars, the gentle pull of the galaxy, the possible influence of Planet 9, all remind us that our solar system is not isolated but embedded in a rich cosmic environment. Every comet that arrives from the Oort cloud carries information about this environment, encrypted in its orbit, written in its composition, revealed in its behavior. 3I Atlas was one such messenger, and though it has now dissolved, the information it carried continues to inform our understanding of the cosmos. We stand now at a threshold, preparing to contemplate what it would mean if Planet 9 truly exists, if our solar system harbours a massive world we've somehow overlooked. But we approach this contemplation with the wisdom gained from considering alternatives, with the recognition that the universe rarely offers simple answers, with the humility that comes from acknowledging how much we still don't know about our cosmic neighbourhood. The whispers in the dark continue, and we continue to listen, knowing that each whisper might carry a different message, tell a different story, or reveal a different truth about the nature of our solar system. The possibility that our solar system contains a massive undiscovered planet forces us to reconsider everything we thought we knew about our cosmic neighbourhood. If Planet 9 exists, it means we've been living with an incomplete map of our own backyard for all of human history, that every model of the solar system in every textbook and every museum is missing a major component, that our home is fundamentally different from what we believed. This isn't just about adding another entry to a list of planets. It's about recognizing that our solar system is still capable of profound surprises, that there are still new worlds to discover not light years away but right here, orbiting our own sun. To truly appreciate what Planet 9 would mean for our understanding of the solar system, we need to first acknowledge how radically our picture of home has evolved over time. For most of human history, the solar system consisted of what could be seen with the naked eye: the sun, moon, 5 planets, and the stars, which were thought to be fixed on a celestial sphere. The invention of the telescope revealed that those points of light were worlds, that some had moons, that the solar system was vastly larger than previously imagined. The discovery of Uranus in 1781 doubled the known size of the solar system overnight. Neptune's discovery in 1846 showed that we could find planets through mathematics and gravity before we could see them. Pluto's discovery in 1930 and subsequent reclassification taught us that the outer solar system was populated with numerous icy worlds, not just a single planet. Each of these discoveries required us to expand our conception of home. Planet 9 would represent perhaps the most dramatic expansion yet, not just because of its size, 10 times Earth's mass, but because of what its existence would imply about planetary formation and migration. Current models of solar system formation struggle to explain how such a massive planet could form so far from the Sun. There simply isn't enough material in the protoplanetary disk at those distances to build a planet that large through traditional accretion. This means Planet 9, if it exists, must have formed elsewhere and migrated to its current orbit, or perhaps even more remarkably, been captured from another star system entirely. The implications of Planet 9 for planetary formation theory extend beyond just our solar system. When we look at exoplanetary systems, we often find super-Earths and mini-Neptunes, planets in the size range between Earth and Neptune. These appear to be the most common types of planets in the universe, yet our solar system apparently lacks any planets in this size range. Planet 9 would fill this gap, making our solar system more typical, more representative of planetary systems in general. It would suggest that super-Earths aren't absent from our solar system. We just haven't found ours yet. The existence of Planet 9 would also reshape our understanding of the solar system's architecture. Currently, we think of the solar system as having a fairly clean structure: rocky planets close to the Sun, gas giants farther out, and then a disk of small, icy bodies beyond Neptune. Planet 9 would add a new zone to this structure, a realm of distant giant planets that we never knew existed. It might not be alone out there. If one massive planet has escaped detection, there could be others, perhaps smaller or more distant, waiting to be discovered. Consider what Planet 9 would mean for our understanding of the Kuiper Belt and the scattered disk. These regions, populated with thousands of small icy bodies, have orbits that tell stories of gravitational interactions with the giant planets. The unusual orbits of objects like Sedna, with their extreme distances and high inclinations, have been puzzles that Planet 9 might solve. If confirmed, Planet 9 would become the dominant gravitational sculptor of the outer solar system, the architect of orbital patterns we've observed but couldn't explain. The discovery of Planet 9 would trigger a renaissance in solar system astronomy. Suddenly, every observation of the outer solar system would need to be reinterpreted in light of this new massive perturber. Graduate students would write dissertations on Planet 9's influence on various populations of small bodies. Space agencies would begin planning missions to explore this new world. The planet would need a proper name, sparking debates about mythology and cultural representation. It would become a target for science fiction writers, a destination for future human exploration, a new frontier for our species to contemplate. But Planet 9 would also be a world of extremes, unlike anything else in our solar system. At its predicted distance, noon on Planet 9 would be dimmer than twilight on Earth. The Sun would appear as merely the brightest star, providing virtually no warmth. If the planet has an atmosphere, it would likely be frozen solid on the surface, creating landscapes of nitrogen or methane ice. The planet might have captured moons, worlds that would be even colder and darker, locked in eternal night. It would be a realm so alien that it would challenge our Earth-centered concepts of what a planet can be. The technological achievement that the discovery of Planet 9 would represent cannot be overstated. Finding a dark world potentially hundreds of billions of miles away, moving slowly against a background of millions of stars, would be a triumph of human ingenuity. It would validate decades of patient observation, sophisticated mathematical modeling, and technological development. It would show that even in an age of exoplanet discoveries and gravitational wave detections, there are still fundamental discoveries to be made in our own solar system. The psychological impact of Planet 9's discovery would be profound. For children learning about the solar system, there would be 9 major planets again, though the 9th would be nothing like the Pluto their parents might remember. For astronomers, it would be a reminder that our catalogues and surveys are still incomplete, that there are still major objects waiting to be discovered. For humanity as a whole, it would be a humbling reminder of how much we still don't know about our cosmic neighbourhood. Planet 9 would also raise profound questions about the solar system's past. How did it get to its current orbit? If it migrated from the inner solar system, what caused that migration? How did the other planets respond to its movement? If it was captured from another star, when did that happen? And what was our solar system like before its arrival? These questions would drive research for decades, spawning new models of solar system evolution, new interpretations of lunar and planetary cratering records, new understanding of the delivery of water and organics to the inner planets. The astrobiological implications of Planet 9 deserve consideration. If the planet has been sending comets toward the inner solar system for billions of years, it might have played a crucial role in the development of life on Earth. Comets are thought to have delivered water and organic molecules to the early Earth. If Planet 9 increased the flux of comets, it might have accelerated the delivery of these life-essential materials. Alternatively, if Planet 9 triggered comet showers that caused mass extinctions, it might have repeatedly reset the evolutionary clock, shaping the trajectory of life on Earth in profound ways. The existence of Planet 9 would also affect our search for life elsewhere in the solar system. If the planet has moons, they would become targets for astrobiological investigation, though the extreme cold and darkness would make life as we know it extremely unlikely. More interestingly, Planet 9's gravitational influence might have affected the delivery of organics to other worlds in the solar system, potentially influencing the habitability of Mars, Europa, Enceladus, and other targets of astrobiological interest. From a philosophical perspective, Planet 9 would remind us that reality doesn't care about our expectations or preferences. We've organized the solar system into neat categories: inner planets, outer planets, dwarf planets, asteroids, comets. But nature doesn't respect our categories. Planet 9 would be a giant planet in a region where we didn't expect giant planets, following an orbit that challenges our theories of planetary formation. It would be a reminder that the universe is under no obligation to conform to our models. The cultural impact of discovering Planet 9 would ripple far beyond astronomy. It would be front-page news worldwide, a rare moment when astronomy captures global attention. It would inspire a new generation of scientists and explorers. It would appear in updated textbooks, planetarium shows, and museum exhibits. Science fiction writers would imagine future missions to this dark world, perhaps even colonization attempts. Artists would create impressions of what the planet might look like, what views it might offer of the distant sun and stars. Planet 9 would also raise questions about what else we might have missed. If a planet 10 times Earth's mass has escaped detection, what other large objects might be lurking in the outer darkness? Could there be a brown dwarf companion to the Sun, too faint and distant to detect with current technology? Might there be captured interstellar planets orbiting far beyond Planet 9? The discovery would remind us that absence of evidence is not evidence of absence, that our surveys of the solar system are far from complete. The search for Planet 9 has already advanced our capabilities in ways that benefit astronomy broadly. The techniques developed to find faint, slow-moving objects in the outer solar system have applications for detecting potentially hazardous asteroids, studying the Kuiper Belt, and searching for other undiscovered objects. The computational methods used to model Planet 9's gravitational influence have advanced our understanding of celestial mechanics. The international collaboration required for the search has strengthened ties between astronomical communities worldwide. If Planet 9 is eventually discovered, the story of its discovery will become a classic tale in the history of astronomy. Like the discovery of Neptune, it will be celebrated as a triumph of theoretical prediction confirmed by observation. The astronomers involved will become famous, their names remembered alongside Herschel, Galler, and Tombaugh. But perhaps more importantly, it will be remembered as a discovery that showed us how much we still had to learn about our own solar system. The possibility that Planet 9 might not exist is also instructive. If, after exhaustive searches with increasingly powerful telescopes, we find no planet, we'll need to explain the orbital alignments and other anomalies through different mechanisms. Perhaps our understanding of gravity on large scales needs refinement. Perhaps there are multiple smaller objects creating the observed effects. Perhaps the alignments are just statistical flukes that will disappear as we discover more objects. Even a null result would advance our understanding. The impact of Planet 9 on future space exploration would be substantial. A new giant planet would become a prime target for robotic exploration, though missions would take decades or centuries to reach it with current technology. The development of faster propulsion systems might be accelerated by the desire to explore this new world within a human lifetime. Planet 9 could become the ultimate destination for crewed missions in the far future, a journey that would dwarf all previous human expeditions in distance and duration. The economic implications of Planet 9 might seem abstract, but they're real. The discovery would likely trigger increased funding for astronomical research, new telescope construction, and space missions. It would create opportunities for education and public outreach. Meteorites or comet samples that might have been influenced by Planet 9 would become more valuable for research. The planet would become part of our cultural heritage, appearing in everything from jewelry designs to corporate logos. Planet 9 would also affect our perspective on Earth's place in the solar system. Currently, Earth occupies the third orbit from the Sun, a special position in the habitable zone where liquid water can exist. With Planet 9 added to the solar system's roster, Earth's position would seem even more special. A tiny warm oasis in a solar system that extends far into the cold darkness. It would underscore both the uniqueness of our world and its vulnerability in a cosmos full of massive objects and chaotic dynamics. The generational aspect of Planet 9 is worth considering. If discovered, it would be the first new planet found in the solar system since 1930, not counting the reclassified dwarf planets. Most people alive today have lived their entire lives with a fixed idea of how many planets orbit the Sun. The discovery would mark a generational moment, dividing those who grew up with 8 planets from those who will grow up with 9 or more. It would be a shared global experience of discovery, something increasingly rare in our fragmented media landscape. The technical challenges of studying Planet 9, even after discovery, would be immense. At its distance, even our most powerful telescopes would struggle to resolve surface features. Determining its composition, internal structure, and whether it has moons would require observations at the limit of our capabilities. It might drive the development of new technologies, larger telescopes, more sensitive instruments, perhaps even new types of observations we haven't yet imagined. Planet 9 would also provide a natural laboratory for studying planetary physics under extreme conditions. Its interior would be subject to pressures and temperatures different from any other planet in our solar system. Its atmosphere, if it has one, would exhibit chemistry and dynamics unlike anything we've observed. Its magnetosphere, if it exists, would interact with the solar wind in ways that might surprise us. Every aspect of the planet would provide new data to test and refine our theories of planetary science. The philosophical implications of Planet 9 extend to our understanding of discovery itself. The planet, if it exists, has been there all along, orbiting the Sun for billions of years while human civilization developed, while we invented astronomy, while we discovered the other planets. It would have been there when ancient astronomers first mapped the sky, when Galileo first pointed a telescope at the heavens, when Voyager 2 flew past Neptune. The fact that something so massive could remain hidden for so long would be both humbling and inspiring. As we contemplate what Planet 9 would mean for our understanding of the solar system, we're really contemplating what it means to live in a universe that still holds secrets. Despite our sophisticated technology, our mathematical models, our centuries of observation, there are still fundamental things we don't know about our cosmic home. Planet 9 would be proof that the age of discovery is not over, that there are still new worlds to find, still mysteries to solve, still reasons to look up at the night sky with wonder. The connection between Planet 9 and comets like 3I Atlas adds another dimension to this contemplation. If Planet 9 has been sending comets our way for billions of years, then every comet we've ever observed might need to be reconsidered. Historical comets that change the course of human events, from the comet that appeared before the Battle of Hastings to Halley's Comet's repeated visits, might have been influenced by a planet we didn't know existed. Planet 9 would have been a hidden player in human history, affecting us through the comets it sent our way. Looking to the future, if Planet 9 exists, it will become part of humanity's long-term cosmic perspective. As we eventually spread throughout the solar system, Planet 9 might become an outpost, a gateway to the Oort cloud and interstellar space. Its resources, whatever they might be, could support future expeditions. Its gravity could be used to slingshot spacecraft to incredible speeds. It might become a beacon for interstellar travelers, a marker that says, intelligent life evolved in this system. The search for Planet 9 has already changed how we think about our solar system, even before any discovery. It has shown us that major discoveries are still possible, that our models are incomplete, that mystery and wonder still exist in our cosmic backyard. Whether Planet 9 exists or not, the search itself has value, pushing us to look more carefully, think more creatively, and remain open to possibilities we haven't imagined. As we approach the end of our contemplation of what Planet 9 would mean, we're left with a profound sense of anticipation. Somewhere in the outer darkness, a world 10 times more massive than Earth might be slowly orbiting our sun, waiting to be discovered. Or perhaps it's not there at all, and the patterns we see have some other explanation we haven't thought of yet. Either way, the question remains open, the search continues, and the possibility of discovery keeps us looking outward, wondering what else might be hiding in the darkness. The solar system we never knew might be the solar system we actually live in. Every night, as Earth rotates and new stars rise above the horizon, Planet 9 might be among them, too faint to see with the naked eye, but there nonetheless, continuing its ancient orbit, influencing comets and asteroids, shaping the architecture of our cosmic home. The fact that we don't yet know if it exists makes this moment in history special. We stand at the threshold of potential discovery, living in the last generation that doesn't know whether our solar system contains 9 planets or 8, whether we've mapped our neighborhood or are still missing major landmarks. This uncertainty is not a weakness but a strength. It drives us to keep searching, to build better instruments, to think more carefully about the evidence. It reminds us that science is an ongoing process, not a finished product. The solar system we never knew might be revealed tomorrow, or in a decade, or perhaps never if our theories are wrong. But the search itself enriches us, expands our capabilities, and maintains our connection to the fundamental human drive to explore and understand our place in the cosmos. Now, as we prepare for our final contemplation, we carry with us this vision of a solar system that might be far stranger and more wonderful than we imagined. Whether Planet 9 exists or not, whether 3i Atlas was its messenger or just a random visitor, whether our models are correct or need revision, we're left with a profound appreciation for the ongoing nature of discovery. The questions we ask are as important as the answers we find, and sometimes the most beautiful thing in science is an unanswered question that keeps us searching, wondering and dreaming about what might be waiting in the darkness.